Picture a world so violently hot that it makes the surface of our sun look cool by comparison. A planet where iron doesn't just melt, it boils into vapor and rains from metallic clouds. Where the atmosphere itself is being ripped away into space at thousands of tons per second, screaming into the void as the planet slowly tears itself apart. This isn't some nightmare from science fiction or a distant vision of hell from ancient mythology. This is KELT 9b, a real planet orbiting a real star about 670 light-years from Earth, and it's hands down the most absolutely terrifying world we've ever discovered in our exploration of the cosmos. To truly understand the horror of this world, we must journey back to the moment of its discovery. The story of KELT 9b begins in 2016, though the planet itself had been silently orbiting its star for perhaps billions of years, unknown and unseen by human eyes. The discovery came through the Kilodegree Extremely Little Telescope Survey, a ground-based astronomical survey designed to search for transiting exoplanets around bright stars. The KELT survey consisted of 2 robotic telescopes, one in Arizona and one in South Africa, each equipped with relatively small telephoto lenses that continuously monitored large swaths of the night sky. Unlike the massive observatory telescopes that capture stunning images of distant galaxies, the KELT telescopes were designed for a specific purpose: to detect the tiny dips in stellar brightness that occur when a planet passes in front of its host star from our perspective here on Earth. When astronomers first noticed the peculiar light curve coming from the star catalogued as KELT 9, they knew immediately that something extraordinary was happening. The transit signal showed all the hallmarks of a massive planet passing in front of a very bright, very hot star. But as the data accumulated and follow-up observations were conducted using more powerful instruments, the full picture began to emerge, and it was unlike anything that had been observed before. The planet was massive, the star was incredibly hot, and the orbital period was shockingly brief. Initial spectroscopic analysis revealed temperature readings that seemed almost impossible, numbers that had to be checked and rechecked because they pushed into territory that blurred the line between what we traditionally call a planet and what we call a star. What made KELT 9b stand out immediately among the thousands of exoplanets that had already been catalogued was not just one extreme characteristic, but rather a perfect storm of multiple extreme factors all concentrated in a single world. By 2016, astronomers had discovered planets with highly elliptical orbits, planets tidally locked to their stars, planets with atmospheres being stripped away, and planets orbiting very close to their host stars. But KELT 9b took every one of these extreme characteristics and amplified them to levels never before witnessed. The planet orbited so close to its star that its year lasted less than 2 Earth days. The star itself was so hot that it was classified among the most luminous and energetic stars known to host planets, and the temperatures measured on the planet's surface exceeded those found on the surfaces of many stars throughout the galaxy. The scientific community responded to the discovery with a mixture of excitement and disbelief. Papers were published, observations were replicated by independent teams, and gradually the reality set in. Humanity had discovered a planet that existed in conditions so extreme that it was literally destroying itself in real time. This was not a stable world that might remain in its current state for billions of years. This was a planet caught in a death spiral, a cosmic cautionary tale written across the heavens about what happens when a world finds itself in the wrong place at the wrong time, around the wrong star. To truly comprehend the scale of what we're dealing with when we discuss KELT 9b, we need to examine the raw numbers that define this world, because each statistic tells part of a larger story of cosmic extremity. The planet itself has a mass approximately 3 times that of Jupiter, making it one of the more massive planets yet discovered in our survey of exoplanetary systems. Jupiter, the giant of our own solar system, contains more mass than all the other planets, moons, asteroids, and comets in our solar system combined. Now imagine a world 3 times more massive than that, and you begin to grasp the sheer scale of KELT 9b. This is not some small rocky world like Earth or Mars that could be vaporized quickly. This is a gas giant with immense gravitational pull. Yet even with all that mass, it cannot hold itself together against the forces that assault it. The planet resides approximately 670 light-years from Earth, situated in the constellation Cygnus, the Swan. To put this distance in perspective, if you could travel at the speed of light, which is approximately 186,000 miles per second, it would still take you 670 years to reach this world. Using our current spacecraft technology, such a journey would take tens of millions of years. Yet despite this incredible distance, we can study KELT 9b in remarkable detail through the sophisticated techniques of modern astronomy, analyzing the light from its star as it filters through the planet's atmosphere during transits, breaking that light down into its component wavelengths to reveal the chemical signatures of elements and compounds present in that alien sky. When we compare KELT 9b to Jupiter, the differences extend beyond just mass. Jupiter's radius is approximately 70,000 kilometers, while KELT 9b, despite being more massive, has an even larger radius due to the extreme heating it experiences. The intense stellar radiation heats and inflates the planet's atmosphere, causing it to puff up to dimensions that exceed what its mass alone would suggest. This gives the planet a surprisingly low density for its mass, a characteristic common among hot Jupiters, but taken to an extreme. In KELT 9b's case, the planet's volume is so large relative to its mass that if you could somehow place it in a cosmic ocean, its density would be less than that of water under normal conditions. Though of course, at the temperatures present on KELT 9b, no liquid water could possibly exist. The orbital characteristics of KELT 9b reveal even more about the extreme nature of this world. The planet completes one full orbit around its star in approximately 36 hours. Think about that for a moment. A full year on KELT 9b, from one starting point back to that same starting point in its orbit, takes only 1.5 Earth days. This means that if you could somehow stand on the surface of this world, though you would be vaporized instantly, you would see the star race across the sky at speeds that would be dizzying to contemplate. The rapid orbital period is a direct consequence of the planet's proximity to its star, following the same gravitational laws that govern all orbital mechanics. Laws first described by Johannes Kepler in the early 17th century, but now applied to a system so extreme that Kepler himself could never have imagined it. To understand why KELT 9b exists in such hellish conditions, we must first understand the nature of the star it orbits, because the character of a star fundamentally shapes the environment experienced by any planet in its vicinity. KELT 9, the parent star of this doomed world, is classified as an A-type main sequence star, a classification that immediately tells astronomers a great deal about its properties. A-type stars are significantly more massive than our Sun, typically ranging from about 1.4 to 2.1 times the solar mass. They are also considerably hotter, with surface temperatures that can reach 10,000 Kelvin or even higher. For comparison, our Sun has a surface temperature of approximately 5,800 Kelvin, meaning that KELT 9 is nearly twice as hot as the star that warms our Earth and makes life possible in our corner of the galaxy. The temperature of KELT 9 sits at around 10,000 Kelvin. a figure that has profound implications for any planet unfortunate enough to orbit nearby. At this temperature, the star emits vast amounts of ultraviolet radiation, far more than our Sun produces. This high-energy radiation is capable of breaking apart molecules, stripping electrons from atoms, and generally wreaking havoc on anything in its vicinity. The star's spectral class places it in a category of stars that are relatively rare, making up only about 0.6% of all main sequence stars in our galaxy. These stars burn their fuel much more quickly than cooler stars like our Sun, living fast and dying young on cosmic timescales. While our Sun will remain stable for another 5 billion years or so, A-type stars like KELT 9 exhaust their hydrogen fuel in only a few 100 million to about 1 billion years. The luminosity of KELT 9 is another critical factor in understanding the environment around it. Luminosity refers to the total amount of energy a star emits per unit time, and KELT 9 is vastly more luminous than our Sun. Some estimates suggest it radiates roughly 56 times more energy than our Sun, though the exact figure depends on various factors and measurement techniques. This enormous energy output means that the habitable zone around KELT 9, the region where liquid water could theoretically exist on a planet's surface, lies much farther from the star than Earth's distance from the Sun. Any planet close to KELT 9 is bathed in radiation levels that are almost unimaginable, subjected to an onslaught of photons carrying energies capable of tearing apart chemical bonds and ionizing atoms. The mass of KELT 9 is approximately 2.4 times that of our Sun, making it a truly massive star by the standards of stellar populations. This greater mass means stronger gravitational forces, which in turn affect how the star evolves over time and how it interacts with any planets in its system. The star rotates relatively rapidly for its type, completing a rotation approximately every 16 hours. This rapid rotation can affect the star's magnetic field and its stellar activity, potentially leading to powerful stellar winds and magnetic events that further bombard any nearby planets. The combination of high temperature, high luminosity, rapid rotation, and massive energy output makes KELT 9 a stellar furnace that creates an environment of unparalleled hostility for any planet in close proximity. The relationship between KELT 9b and its star can only be described as a deadly embrace, a cosmic dance so close and so intimate that it is slowly destroying the planet. Orbital mechanics tell us that the closer a planet is to its star, the faster it must travel to maintain a stable orbit, and KELT 9b races around its star at speeds that dwarf anything in our solar system. The planet orbits at a distance of only about 0.03 astronomical units from KELT 9. An astronomical unit is defined as the average distance between Earth and the Sun, approximately 150 million kilometers. This means KELT 9b orbits its star at a distance of only about 4.5 million kilometers. To put this in perspective, Mercury, the closest planet to our Sun, orbits at an average distance of about 58 million kilometers. KELT 9b is more than 10 times closer to its star than Mercury is to the Sun. At this intimate distance, KELT 9b experiences gravitational and radiation forces that are almost beyond comprehension. The gravitational gradient across the planet is extreme, with the side facing the star experiencing significantly stronger gravitational pull than the far side. This differential gravitational force creates tidal effects that heat the planet's interior and likely contribute to the inflation of its atmosphere. The planet is almost certainly tidally locked to its star, meaning the same hemisphere always faces KELT 9, just as the same side of our Moon always faces Earth. This tidal locking is not unusual for planets orbiting so close to their stars. The gravitational forces at play make any other configuration unstable over cosmic timescales. The orbital velocity required to maintain such a close orbit is staggering. KELT 9b must be traveling at hundreds of kilometers per second relative to its star, racing along its orbital path at speeds that make our fastest rockets look motionless by comparison. Every 36 hours, this massive world completes another circuit around KELT 9, another lap in a race it can never win, because the finish line is not survival, but eventual destruction. The orbital distance is so small that if you could somehow replace our Sun with KELT 9 and place KELT 9b in its orbit, the planet would fit well within the orbit of Mercury, closer to the Sun than any planet in our solar system ever ventures. The radiation flux that KELT 9b receives from its star is approximately 40,000 times greater than what Earth receives from the Sun. This number is so large that it's difficult to conceptualize. Every square meter of KELT 9b's dayside is being bombarded with 40,000 times more energy than the same area on Earth receives from our Sun at high noon on the equator. This is not just about visible light. This includes the full spectrum of electromagnetic radiation, from infrared to visible light to ultraviolet and beyond. The ultraviolet radiation alone is enough to break apart nearly any molecular bond, which is why the chemistry of KELT 9b's atmosphere is so radically different from anything we see in our solar system. The geometry of the orbit itself is also significant. While many exoplanets have been discovered with highly elliptical orbits that bring them close to their stars at some points and farther away at others, KELT 9b's orbit appears to be relatively circular. This means there is no respite, no part of its year where the planet swings to a safer distance. Every moment of every day, KELT 9b is subjected to the same relentless assault of radiation and heat. The planet transits its star from our perspective, meaning its orbital plane is aligned such that we see the planet pass in front of the star periodically. These transits are what allowed astronomers to discover and study the planet, as the starlight dimming during each transit and the starlight filtering through the planet's atmosphere. During those transits provide windows into the conditions on this distant world. When we turn our attention to the temperature of KELT 9b, we enter a realm that stretches the boundaries of what we typically associate with planetary environments and begins to overlap with the domain of stars themselves. The dayside temperature of KELT 9b has been measured at approximately 4,600 Kelvin. To put this temperature in perspective, we need to compare it to other astronomical objects and conditions. The surface temperature of our Sun, the star that makes life on Earth possible, is about 5,800 Kelvin. KELT 9b, a planet, has a dayside temperature that is roughly 80% as hot as the Sun's surface. This means that if you could somehow observe KELT 9b and the Sun side by side, the planet would glow nearly as brightly as the star itself. Though of course, we must remember that the Sun's enormous size means it emits vastly more total energy. Even more striking is the comparison between KELT 9b and certain types of stars. Red dwarf stars, also known as M-class main sequence stars, are the most common type of star in our galaxy, making up about 70% of all stars. The coolest red dwarfs have surface temperatures of around 2,300 Kelvin, while the hottest can reach about 3,800 Kelvin. KELT 9b is hotter than all red dwarf stars in the universe. This planet glows more intensely than billions upon billions of stars scattered throughout the cosmos. It is a planet that has transcended its category in terms of temperature, existing in a state that makes it more stellar than planetary in its thermal characteristics. the 4,600 Kelvin temperature represents an average across the dayside hemisphere. In reality, there are likely temperature variations across the surface, with the subsolar point, the location directly, beneath the star at the center of the dayside hemisphere, probably reaching even higher temperatures. Some models suggest that localized temperatures might exceed 5,000 Kelvin in these regions, approaching even closer to the Sun's surface temperature. These are not abstract numbers. They represent real physical conditions with concrete consequences for the matter that exists in such an environment. At these temperatures, solids cannot exist. Liquids cannot exist. Even the molecular structures of gases are torn apart by the sheer thermal energy present. To understand what 4,600 Kelvin really means in practical terms, consider what happens to various materials at these temperatures. Iron, one of the most common elements in rocky planets and a major component of Earth's core, has a melting point of about 1,511 Kelvin and a boiling point of about 3,134 Kelvin. On KELT 9b's dayside, iron would not just be molten, it would be vaporized into a gas, with individual atoms floating freely in the atmosphere. Silicon dioxide, the primary component of sand and rock on Earth, breaks down completely at these temperatures. Carbon dioxide, the greenhouse gas that warms Mars and once dominated Earth's ancient atmosphere, cannot exist as a molecule. The carbon and oxygen atoms are ripped apart and exist independently. Water, the molecule essential to all life as we know it, is obliterated, broken down into individual hydrogen and oxygen atoms that float separately in the scorching atmosphere. The night side of KELT 9b, eternally facing away from the star due to tidal locking, experiences dramatically lower temperatures, though still extreme by Earth standards. Estimates suggest the night side might cool to around 2,500 to 3,000 Kelvin, still hot enough to melt rock and vaporize many metals, but relatively cool compared to the dayside inferno. This creates the largest temperature difference between two hemispheres of any known planet, a gradient of perhaps 1,500 to 2,000 Kelvin, from the center of the day side to the center of the night side. This temperature difference drives atmospheric dynamics of incredible violence, creating winds and weather patterns that make Earth's hurricanes look like gentle breezes. The extreme temperatures on KELT 9b result directly from the combination of the star's properties and the planet's proximity. The intense radiation from KELT 9 delivers energy to the planet's atmosphere faster than the atmosphere can radiate it away into space. On Earth, incoming solar radiation is balanced by outgoing infrared radiation, maintaining a relatively stable average. Temperature. On KELT 9b, this balance is completely overwhelmed on the day side. The planet receives so much energy that it heats to temperatures where it glows visibly, emitting its own light in addition to reflecting light from the star. This makes KELT 9b one of the few planets that could theoretically be directly imaged by powerful enough telescopes, not just detected indirectly through transits or gravitational effects, because the planet itself shines brightly enough to be seen against the darkness of space. At the temperatures found on KELT 9b, matter behaves in ways that are foreign to our everyday experience, but familiar to physicists who study stellar interiors and extreme states of matter. The concept of molecular dissociation becomes central to understanding what happens in the atmosphere of this hellish world. In normal conditions, atoms bond together to form molecules, sharing or transferring electrons to create stable configurations that minimize energy. Water, for instance, consists of two hydrogen atoms bonded to one oxygen atom, forming a molecule with specific properties that we encounter every day. Carbon dioxide consists of one carbon atom bonded to two oxygen atoms. Hydrogen gas, the most common molecule in the universe, consists of two hydrogen atoms bonded together. These molecular bonds have specific energies holding them together, and when the thermal energy in an environment exceeds these bond energies, the molecules simply fall apart. On the day side of KELT 9b, the temperatures are so high that essentially no stable molecules can exist. The thermal energy in the atmosphere, represented by the random motion of particles bouncing and colliding at incredible speeds, overwhelms the electromagnetic forces that would normally hold atoms together in molecular structures. Water molecules, if they somehow formed, would be ripped apart in a tiny fraction of a second. Carbon dioxide would immediately dissociate into individual carbon and oxygen atoms. Even nitrogen molecules, which have one of the strongest molecular bonds among common atmospheric constituents, cannot remain intact. The day-side atmosphere consists not of molecules, but of individual atoms, each one moving independently at velocities of several kilometers per second, colliding with one another in a chaotic dance of thermal energy. Perhaps most remarkably, even molecular hydrogen, the most abundant molecule in the universe and typically extremely stable, cannot survive on KELT 9b's dayside hydrogen molecules consist of two hydrogen atoms bonded together, and this bond is relatively strong by molecular standards. Throughout most of the universe, in nebulae, in the atmospheres of gas giant planets, in interstellar space, hydrogen exists primarily in molecular form. But on KELT 9b, the temperatures are high enough to break this fundamental bond. Observations have confirmed that on the dayside hemisphere, hydrogen exists primarily in atomic form, with individual hydrogen atoms floating freely rather than pairing up into molecules. This is the signature of truly extreme conditions, as breaking the hydrogen molecular bond requires temperatures typically found only in stellar atmospheres or in the most extreme planetary environments. The process of molecular dissociation is not instantaneous or uniform across the planet. As atoms are carried by winds from the cooler night side toward the day side, molecules that may have formed in the cooler regions begin to experience increasing temperatures. At some point in this journey, as temperatures climb past certain thresholds, different molecules begin to break apart. Simpler molecules with weaker bonds dissociate first, then progressively stronger molecules break apart as temperatures continue to rise. By the time atmospheric gases reach the subsolar point, the hottest region on the planet, essentially complete dissociation has occurred, and the atmosphere consists almost entirely of individual atoms rather than molecular species. This dissociation has profound effects on the atmospheric chemistry and physics of KELT 9b. The chemical reactions that can occur in a molecular atmosphere are vastly different from those possible in an atomic atmosphere. On Earth, atmospheric chemistry involves complex molecules reacting with one another, forming new compounds through processes driven by solar radiation, temperature changes, and catalytic effects. On KELT 9b's dayside, chemistry, in the traditional sense, barely exists. Instead, you have atomic collisions that might occasionally result in ionization, where electrons are stripped from atoms by the sheer energy of impact, creating a partially ionized gas or plasma. The atmosphere takes on some characteristics of a stellar atmosphere rather than a planetary one, with conditions more similar to what we would find in the outer layers of a cool star than in any planetary atmosphere in our solar system. The dissociation process also affects how the atmosphere absorbs and emits radiation. Molecules have complex structures that allow them to absorb light at specific wavelengths determined by their vibrational and rotational energy levels. This gives molecular atmospheres their characteristic absorption spectra, with specific dark lines appearing at wavelengths where molecules absorb light. Atoms, in contrast, have simpler absorption spectra, determined only by the electronic transitions between different energy levels. The spectrum of KELT 9b shows strong atomic absorption lines, but lacks the molecular features that characterize most planetary atmospheres. This atomic spectrum is one of the key signatures that astronomers use to confirm the extreme temperatures on this world and to determine the composition of its atmosphere. When atoms are dissociated from molecules, they are also more susceptible to being ionized, having electrons stripped away completely by high-energy ultraviolet photons from the star, or by collisions with other particles. Some models suggest that the upper atmosphere of KELT 9b may be partially ionized, creating a plasma where a significant fraction of atoms have lost one or more electrons. This ionized layer would interact strongly with the stellar magnetic field and the stellar wind, potentially creating complex magnetospheric phenomena, unlike anything seen in our solar system. The ionization also affects how the atmosphere responds to the stellar radiation, with ionized gases absorbing and emitting light differently than neutral atoms would. One of the most dramatic consequences of KELT 9b's extreme temperature and radiation environment is that the planet is quite literally tearing itself apart, losing thousands of tons of atmospheric material to space every single second in a process called atmospheric evaporation or hydrodynamic escape. This is not the gentle, gradual loss of atmosphere that Mars experienced over billions of years, nor is it similar to the solar wind slowly stripping away Earth's upper atmosphere at a rate that is barely measurable. This is catastrophic. Mass loss occurring in real time, a planetary scale hemorrhaging of gas into the void of space that is fundamentally changing the planet as we observe it. The mechanism driving this atmospheric evaporation involves several interconnected processes. First, the intense stellar radiation heats the upper atmosphere to extreme temperatures, giving atoms and ions tremendous kinetic energy. When particles in a gas move fast enough, they can escape the gravitational pull of the planet entirely, flying off into space never to return. On Earth, this only happens to the lightest atoms like hydrogen and helium, and even then, only from the very highest layers of our atmosphere, where particles rarely collide with one another. On KELT 9b, the temperatures are so high that even heavier elements gain enough energy to escape, and the escape occurs from much deeper in the atmosphere because the entire atmospheric column is so hot. The ultraviolet radiation from KELT 9 plays a crucial role in driving this atmospheric evaporation. High-energy ultraviolet photons are absorbed by atoms in the upper atmosphere, providing them with additional energy that can help them overcome the planet's gravity. This absorption also heats the upper atmosphere to even higher temperatures than would be reached by thermal radiation alone. Some of the ultraviolet photons are energetic enough to ionize atoms, stripping away electrons and creating charged particles. These ions can interact with the stellar magnetic field and be accelerated to even higher velocities, potentially being driven away from the planet by magnetic forces in addition to thermal processes. Observations of KELT 9b have revealed a massive extended atmosphere surrounding the planet, essentially a cloud of escaping gas that extends far beyond the planet's surface. When the planet transits in front of its star, this extended atmosphere blocks additional starlight, creating a transit signature that is larger than the planet itself would produce. By studying how the transit depth changes at different wavelengths of light, astronomers can probe the structure and composition of this escaping atmosphere. The observations show clear evidence of hydrogen, helium, and other elements streaming away from the planet, in what amounts to a planetary wind. Though calling it a wind hardly does justice to the scale and violence of this process. Current estimates suggest that KELT 9b is losing mass at a rate of somewhere around 10,000 to 100,000 metric tons per second, though the exact rate is difficult to pin down and likely varies depending on the star's activity level and other factors. Even taking a middle estimate of perhaps 50,000 metric tons per second, this amounts to over 4 billion metric tons of atmospheric material lost every day. That's roughly equivalent to losing the mass of a small asteroid every 24 hours. Over 1 million years, this adds up to more than 10 to the 18th power kilograms, a truly astronomical amount of material. Yet because KELT 9b is so massive, containing perhaps 6 times 10 to the 27th power kilograms in total, this mass loss, while dramatic, has not yet stripped away a significant fraction of the planet's total mass over its lifetime. However, the mass loss rate may not remain constant over time. As the planet continues to lose its lighter atmospheric components, the average molecular weight of the remaining atmosphere may increase, potentially slowing the escape rate. Conversely, as the planet spirals closer to its star over time due to tidal effects, the stellar radiation intensity will increase, potentially accelerating the mass loss. The interplay between these factors makes it difficult to predict the long-term evolution of KELT 9b's mass loss. But one thing is certain: the planet is slowly but inexorably being consumed by its environment, evaporating into space like a slowly melting ice cube on a hot summer day. Except that this ice cube is the size of Jupiter, and the hot summer day has temperatures rivaling those on the surface of stars. The atmospheric evaporation also has interesting observational consequences. The escaping material forms a tail extending behind the planet in its orbit, similar to a comet's tail, but composed of hot gas rather than ice and dust. This tail of escaping atmosphere can potentially be detected through careful observations, providing additional information about the composition and behavior of the evaporating material. Some of this material may eventually fall back onto the star itself, polluting the stellar atmosphere with heavy elements that originally came from the planet. In this way, KELT 9b is not just being destroyed by its star, it is actually changing the star's composition, however slightly, through the transfer of material from planet to star. The extreme temperatures and atmospheric conditions on KELT 9b create an environment where exotic chemistry occurs. Chemistry involving elements that we normally think of as solid metals, or that we associate with rocks and minerals rather than with gases floating in an atmosphere. The detection of vaporized metals in KELT 9b's atmosphere represents one of the most striking confirmations of the planet's extreme conditions, and provides a window into chemistry that cannot be studied in any laboratory on Earth. When we talk about metals in this context, we are referring to elements from across the periodic table that we normally encounter as solid, shiny substances with high melting and boiling points. Yet on KELT 9b, these refractory elements exist as gases, floating freely in an atmosphere that bears little resemblance to any planetary atmosphere in our solar system. Spectroscopic observations of KELT 9b have revealed the presence of atomic iron and atomic magnesium in the atmosphere, confirmed through the detection of their characteristic absorption lines in the starlight that passes through the planet's atmosphere during transits. Iron, with a boiling point of 3,134 Kelvin at standard pressure, normally requires temperatures found in the cores of rocky planets or in the hottest industrial furnaces to vaporize. On KELT 9b, iron vapor exists as a normal atmospheric constituent, with iron atoms floating alongside hydrogen, helium, and other elements in the scorching atmosphere. Magnesium, which boils at about 1363 Kelvin, is even more readily vaporized under these conditions. But iron and magnesium are just the beginning. Further observations have revealed an increasingly exotic cocktail of elements present in vapor form. Sodium and potassium, alkali metals with relatively low boiling points compared to transition metals, are present in large quantities. Calcium, another element we typically associate with solid minerals and bones, floats as atomic vapor in the atmosphere. Chromium, titanium, scandium, nickel, and even ionized calcium have been detected, each discovery adding to the picture of an atmosphere whose composition reads more like a catalogue of the periodic table than like the simple molecular atmospheres of planets in our solar system. The presence of these vaporized metals has profound effects on the atmosphere's properties and behavior. Metals are excellent absorbers of radiation across a wide range of wavelengths, particularly in the visible and ultraviolet regions of the spectrum. The presence of metal vapor means that KELT 9b's atmosphere can absorb stellar radiation very efficiently, contributing to the high temperatures and affecting how energy is distributed throughout the atmosphere. The metal atoms can also re-emit radiation after absorbing it, though at the extreme temperatures present, most of the absorbed energy goes into heating the atmosphere further rather than being radiated away efficiently. This creates a feedback loop where metal vapor helps heat the atmosphere, which in turn keeps the metals in vapor form. The spatial distribution of these metals in the atmosphere is not uniform. Because KELT 9b is tidally locked, with one side perpetually facing the star and the other in eternal darkness, there is a strong temperature gradient across the planet. The metals vaporize on the hot day side, where temperatures are high enough to keep them in gaseous form. These metal vapors are then carried by powerful winds toward the cooler night side. As they move to cooler regions and temperatures drop below their condensation points, the metals begin to condense out of the gas phase. On the night side, iron and other refractory elements may actually form metallic clouds, with tiny droplets or particles of liquid and solid metal suspended in the atmosphere, similar to water clouds on Earth, but composed of materials we would normally think of as construction materials or jewelry, rather than weather phenomena. This process creates a remarkable cycle of vaporization and condensation. Metals evaporate on the day side, are carried to the night side by atmospheric winds, condense into metallic clouds or rain, fall deeper into the atmosphere where temperatures are higher, vaporize again, and are carried back toward the day side to repeat the cycle. This is fundamentally different from the water cycle on Earth, but it operates on similar principles. Instead of water evaporating from oceans and condensing into clouds, we have iron evaporating from the deeper atmosphere and condensing into metallic clouds. Some models even suggest the possibility of iron rain on the night side of KELT 9b, with droplets of liquid iron falling through the atmosphere, though the extreme conditions make it difficult to definitively confirm whether such rain actually occurs. The detection of these vaporized metals has been possible through extremely precise spectroscopic observations. During transits, when KELT 9b passes in front of its star from our perspective, a tiny fraction of the starlight passes through the planet's atmosphere before reaching Earth. This light carries the fingerprints of the atoms it encountered during its journey through the atmosphere. Each element absorbs light at specific wavelengths determined by the quantum mechanical properties of its electrons, and by carefully analyzing the spectrum of the starlight, astronomers can identify which elements are present in the atmosphere and even estimate their abundances. These observations require extremely sensitive instruments capable of detecting changes in brightness of less than 1% at specific wavelengths. but modern spectrographs attached to large telescopes have made such measurements routine for bright transiting systems like KELT 9. The exotic chemistry occurring in KELT 9b's atmosphere also includes the formation and destruction of unusual molecular and ionic species in the cooler regions where molecules can briefly exist before being dissociated again. Some models predict the presence of molecular species like titanium oxide and vanadium oxide in the atmosphere, molecules that play important roles in the atmospheres of cool stars but are rarely considered in planetary contexts. These molecules can form in cooler regions and may contribute to the atmosphere's opacity and thermal structure. The presence of partially ionized species adds another layer of complexity, as ions interact differently with radiation and magnetic fields than neutral atoms do, potentially creating regions of the atmosphere with drastically different properties. The study of vaporized metals in KELT 9b's atmosphere has implications beyond just understanding this one planet. By observing chemistry at these extreme temperatures, astronomers gain insights into processes that occur in stellar atmospheres and in the early evolution of planetary systems, when temperatures throughout protoplanetary disks were much higher than they are today. The condensation of metals from vapor to solid particles is thought to be one of the first steps in planet formation, and by observing this process, occurring in real time on KELT 9b, albeit in reverse, scientists can test models of how solid materials originally formed in our own solar system billions of years ago. In this sense, KELT 9b serves as a natural laboratory for studying high-temperature chemistry and physics that would be impossible to replicate in any Earth-based facility. The tidal locking of KELT 9b, where one hemisphere perpetually faces its star while the opposite hemisphere remains in eternal darkness, represents one of the fundamental factors that shapes every aspect of this planet's environment and creates some of its most extreme characteristics. Tidal locking occurs when gravitational interactions between a planet and its star over long periods of time synchronize the planet's rotational period with its orbital period. This is the same phenomenon that causes Earth's moon to always show us the same face, and it is extremely common among planets that orbit close to their stars. For KELT 9b, with its incredibly tight orbit, bringing it within a few million kilometers of its star, tidal locking was probably established very early in the planet's history, perhaps within the first few million years after formation. The mechanism behind tidal locking involves the deformation of the planet due to gravitational forces. The side of the planet facing the star experiences slightly stronger gravitational pull than the center of the planet, and the far side experiences slightly weaker pull. This differential force creates tidal bulges, elongating the planet slightly along the axis, pointing toward the star. If the planet is rotating, these tidal bulges try to remain aligned with the star, but are carried along by the planet's rotation, creating a situation where the bulges are slightly misaligned from the star-planet axis. This misalignment allows the star's gravity to exert a torque on the planet, gradually slowing its rotation over time until the rotational period matches the orbital period and the bulges remain permanently aligned with the star. For KELT 9b, tidal locking has created a permanent division of the planet into three distinct regions: the day-side hemisphere that faces the star, the night-side hemisphere that faces away into eternal darkness, and the terminator region that exists in perpetual twilight, separating these two extremes. Each of these regions has fundamentally different conditions, creating what amounts to three different worlds within a single planet. The day side experiences the full fury of KELT 9's radiation, heated to those extraordinary temperatures of 4,600 Kelvin or higher. This hemisphere is bathed in constant starlight, never experiencing night, never knowing respite from the bombardment of photons and charged particles. The surface, if we can even call it that on a gas giant, is a roiling inferno where atoms move at kilometers per second and no molecule can survive intact. The tidal locking creates stability in one sense, as the same hemisphere always faces the same direction, but it also creates instability through the extreme temperature gradients it produces. The difference between the hottest regions on the day side and the coolest regions on the night side may exceed 2000 Kelvin, one of the largest temperature differences anywhere in the universe for a single planetary body. On Earth, the temperature difference between the hottest deserts and the coldest polar regions is perhaps 150 degrees Celsius, or about 150 Kelvin. KELT 9b, the temperature difference is more than 10 times larger, creating atmospheric dynamics of staggering intensity as the atmosphere attempts to redistribute heat from the scorching day side to the cooler night side. The terminator region, the boundary between permanent day and permanent night, exists in a state of perpetual twilight. Here, the star hangs forever on the horizon, neither rising nor setting, casting long shadows across atmospheric features and creating conditions intermediate between the extremes of the two hemispheres. The temperature gradient is steepest in this region, with temperatures changing by hundreds of Kelvin over relatively short distances as measured along the planet's surface. This creates powerful shear forces in the atmosphere, with winds accelerating dramatically as they flow from the day side toward the night side, or vice versa. The terminator region is likely a zone of intense turbulence, with complex wind patterns, eddies, and possibly even storm systems that dwarf anything in our solar system. The permanent configuration of tidal locking also means that any geological or atmospheric features that might exist on KELT 9b occupy fixed positions relative to the star. If there are regions where atmospheric circulation creates persistent storm systems or zones of enhanced cloud formation, these features would remain in the same locations, unlike weather systems on Earth that move across the globe. This creates the possibility of studying persistent atmospheric phenomena over long timescales, as the same features rotate into and out of view during each 36-hour orbit. Astronomers can potentially map the atmospheric structure of KELT 9b by observing how its brightness changes at different points in its orbit, building up a picture of which regions are hotter or cooler, which regions have more or less metal vapor in, their atmospheres, and how these patterns remain stable or change over multiple orbits. The tidal forces that created the locking continue to affect KELT 9b even after synchronous rotation has been achieved. The tidal bulges raised on the planet by the star's gravity contain enormous amounts of energy, and the dissipation of this energy as heat contributes to the planet's overall energy budget. Some of this tidal heating occurs deep within the planet's interior, potentially creating internal heat sources that add to the external heating from stellar radiation. The tidal forces also work to circularize the orbit over time. Though KELT 9b's orbit already appears to be quite circular based on observations, the ongoing tidal interaction gradually causes the planet to spiral inward toward the star, a process that will eventually lead to the planet's destruction, though the timescale for this inward migration is measured in hundreds of millions of years. The psychology of imagining what it would be like to observe KELT 9b from close proximity is both fascinating and terrifying. If you could somehow approach the planet in a spacecraft immune to its radiation and heat, you would see a glowing orb that shines with its own light, not just reflecting starlight, but radiating energy from its extreme temperature. The day side would glow with a blue-white light, similar to the light from a hot star or an arc welder, bright enough to be painful to look at directly. The night side would be much dimmer, but still hot enough to glow a deep red, like heated metal in a forge. The terminator region would show a gradient of colors from the blue-white of the day side through various shades of white, yellow, and orange to the deep red of the night side. Watching KELT 9b from a safe distance in its orbit, you would see the star and planet locked in their tight embrace, the planet racing around the star at speeds that would make each orbit visible over the course of about a day and a half. If you could somehow survive on the planet's surface, tidally locked to face the star, you would see KELT 9 hanging motionless in the sky, an enormous blue-white disk, many times larger than the Sun appears from Earth, blazing with an intensity that would vaporize any unprotected matter in seconds. The star would never move, never set, never allow darkness to fall. This is a world where the concept of day and night, as we understand it, has no meaning, replaced by a permanent binary division between eternal day and eternal night. While the day side of KELT 9b has been extensively studied and its extreme conditions are relatively well understood, the night side remains more mysterious, a dark hemisphere where temperatures drop to levels that are merely extremely hot rather than apocalyptically hot, creating conditions that allow for different chemical and physical processes to occur. Understanding the night side is crucial for building a complete picture of KELT 9b's atmospheric circulation, chemistry, and evolution. Yet, observing this hidden hemisphere directly is extremely challenging because by definition, it does not face the star and therefore does not transit, limiting the observational techniques available to study it. The night side temperature is estimated to be around 2,500 to 3,000 Kelvin based on theoretical models of atmospheric heat transport, though direct measurements are difficult to obtain. This is still hot enough to melt rock and vaporize many substances, but it represents a dramatic cooling compared to the day side. At these temperatures, some molecular species may be able to form temporarily, though the exact chemistry is complex and depends on many factors, including atmospheric pressure, composition, and the timescales for chemical reactions, versus the timescales for atmospheric transport. The night side represents a transitional regime where the atmosphere begins to take on some characteristics more familiar from other hot Jupiter planets, though still far more extreme than anything in our solar system. One of the key questions about KELT 9b's night side is whether molecules can exist there in significant quantities. As we discussed earlier, the day side is too hot for molecules to survive, with even molecular hydrogen being dissociated into atoms. But on the night side, temperatures are low enough that molecular hydrogen should be able to reform, with hydrogen atoms combining to create H2 molecules. This recombination releases energy, contributing to the night side's heat budget and potentially affecting the atmospheric structure. Other molecules might also form, particularly in the coolest regions, carbon monoxide, with a very strong molecular bond, might persist even at these elevated temperatures. Some metal-bearing molecules, like titanium oxide, might form in localized cooler regions. The question of whether clouds can form on KELT 9b's night side is particularly intriguing. As metal vapors are carried by winds from the hot day side to the cooler night side, they eventually reach temperatures below their condensation points. Iron vapor, for instance, would begin to condense at temperatures around 3,000 Kelvin under the pressures expected in KELT 9b's atmosphere. This means that somewhere in the transition region from day side to night side, iron atoms might clump together to form tiny droplets or solid particles, creating clouds of metal suspended in the atmosphere. These clouds would be unlike anything in our experience, composed not of water or ammonia or methane like clouds elsewhere in the solar system, but of iron, magnesium, silicates, and other refractory materials. If metal clouds do form on the night side, they would have dramatic effects on the planet's appearance and energy budget. Metal particles are excellent absorbers of radiation across most wavelengths, so metal clouds would be highly opaque, blocking the transmission of light through them and affecting how heat is distributed in the atmosphere. The clouds might appear as dark patches against the glowing background of the planet, regions where the underlying hot atmosphere is obscured by overlying condensate. Alternatively, if the cloud particles are suspended at levels where they are still hot enough to emit their own thermal radiation, they might actually add to the planet's overall brightness. The size distribution of the cloud particles, which depends on complex microphysical processes of nucleation and growth, would determine many of their optical properties. The nightside atmosphere might also experience a form of metal rain, where condensed metal droplets grow large enough to fall under gravity, sinking deeper into the atmosphere where temperatures increase and the droplets evaporate again. This would create a vertical cycle of condensation and evaporation, transporting both mass and energy through the atmosphere. The concept of iron rain falling through an atmosphere at 2,500 Kelvin on the night side of a planet 3 times more massive than Jupiter and orbiting a star hotter than our Sun captures the profound alienness of KELT 9b. This is weather in a sense that barely relates to our terrestrial experience of weather. Phenomena governed by the same physical laws we understand from Earth, but operating in regimes where the parameters are so different that the outcomes are almost unrecognizable. The night side might also be the location where any remaining original atmosphere resides. When KELT 9b first migrated to its current close orbit, or if it formed close to the star, it would have initially had a much larger atmosphere. The dayside atmosphere has been stripped away over time by the intense stellar radiation and the hydrodynamic escape process. But material on the night side, shielded from the star's direct radiation, might survive longer. Over time, atmospheric circulation constantly carries material from the night side to the day side, where it can be stripped away. But there is always material on the night side at any given moment, creating a reservoir of atmosphere that is gradually being depleted. Understanding the balance between nightside reservoir, transport to dayside, and escape from dayside is crucial for predicting how long KELT 9b can maintain an atmosphere and what the planet's ultimate fate will be. Observations aimed at characterizing the night side are challenging but possible through careful analysis of the planet's thermal emission. As KELT 9b orbits its star, different hemispheres rotate into and out of view from Earth. When the night side is facing us, the planet's overall thermal emission decreases because we are seeing the cooler hemisphere. By measuring this variation in brightness over the course of the orbit, astronomers can estimate the temperature difference between day and night, and even potentially map the distribution of temperatures across the planet's surface. These observations require extremely sensitive infrared detectors capable of measuring the tiny changes in brightness caused by the planet's rotation. But several research groups have attempted such measurements and have begun to build up a picture of KELT 9b's global climate. The nightside mystery extends to questions about atmospheric stability and dynamics. With such a large temperature gradient driving atmospheric circulation, the night side is the recipient of powerful supersonic winds carrying hot gas from the day side. This creates a situation where the night side is being constantly bombarded by an influx of extremely hot material, while simultaneously trying to radiate energy away to space. The balance between these processes determines the nightside temperature and structure. If heat transport is very efficient, the night side might be heated to temperatures approaching those on the day side, reducing the temperature gradient. If radiative cooling is efficient, or if heat transport is somehow inhibited, the night side could be significantly cooler. Current evidence suggests intermediate behavior, with substantial cooling on the night side, but still temperatures far exceeding anything in our solar system. The atmospheric winds on KELT 9b represent another extreme characteristic of this planet, driven by the enormous temperature difference between the permanent day side and night side created by tidal locking. The atmosphere does not sit passively as one hemisphere is heated to stellar temperatures while the other remains comparatively cool. Instead, powerful winds arise too, transport heat from hot to cold regions, and these winds reach velocities that strain comprehension, transforming the entire atmosphere into a supersonic maelstrom that makes Earth's most violent hurricanes seem like gentle breezes in comparison. Understanding these winds is essential for understanding how KELT 9b functions as a system, and how energy and material are distributed around the planet. The basic mechanism driving winds on KELT 9b is the same as on Earth. Horizontal temperature gradients create pressure gradients, and these pressure differences cause air to flow from high pressure to low pressure regions. On Earth, the sun heats the equator more than the poles, creating temperature differences that drive atmospheric circulation and generate the trade winds, jet streams, and weather systems we experience. But the temperature difference from Earth's equator to its poles is modest, perhaps 60 degrees Celsius on average. And this relatively small gradient drives winds that typically range from gentle breezes to perhaps 200 kilometers per hour in the most intense storms. On KELT 9b, the temperature difference between day side and night side is around 1,500 to 2,000 Kelvin, 10 to 15 times larger than Earth's equator to pole gradient, and this drives winds of proportionally greater intensity. Theoretical models of KELT 9b's atmospheric circulation suggest that wind speeds of several kilometers per second are likely. To put this in perspective, the speed of sound at the temperatures present in KELT 9b's atmosphere is around 2 to 3 kilometers per second, depending on the atmospheric composition and temperature. This means the winds on KELT 9b are supersonic, exceeding the speed of sound and creating shock waves where fast-moving air rams into slower regions. On Earth, supersonic flows only occur in specialized circumstances like jet engines or spacecraft re-entry, where enormous amounts of energy are expended to accelerate gas to such speeds. On KELT 9b, supersonic winds are the norm, a natural consequence of the extreme temperature gradients present. The dominant pattern of circulation on KELT 9b is likely an equatorial jet stream, a high-speed river of gas that circles the planet along or near the equator. This jet forms because the strongest heating occurs at the equatorial subsolar point, the location on the dayside equator directly beneath the star. Atmospheric gas heated at this point rises and flows away from the subsolar point at high altitude, heading toward the night side. As this gas moves, it is deflected by the Coriolis effect, a consequence of the planet's rotation. Although KELT 9b is tidally locked to its star, it still rotates once per orbit, completing a rotation every 36 hours, and this rotation generates Coriolis forces. The deflection causes flows to curve, and the net result is the formation of a powerful jet stream that races around the planet at high speed. This equatorial jet carries hot gas from the day side to the night side, transporting energy and helping to moderate the temperature difference between hemispheres. Along the way, the gas cools somewhat through radiation to space, and the flow patterns become increasingly complex as the gas reaches the night side and begins to descend. The descending gas on the night side creates its own complex flow patterns, with some material flowing back toward the day side at lower altitudes, completing a circulation cell. Multiple circulation cells might exist at different latitudes, with flows at the poles potentially quite different from equatorial flows. The three-dimensional structure of these circulation patterns is one of the most challenging aspects of modeling KELT 9b's atmosphere, requiring sophisticated computer simulations that solve the equations of fluid dynamics under extreme conditions. The supersonic nature of these winds has important consequences for the atmospheric structure and chemistry. When supersonic gas encounters obstacles or slower moving gas, shock waves form. These shocks compress and heat the gas even further, creating localized hotspots that may reach even higher temperatures than the surrounding atmosphere. The shocks also create regions of enhanced turbulence and mixing, potentially stirring the atmosphere and affecting how chemical species are distributed. The energy dissipated in these shocks contributes to the overall heating of the atmosphere, creating a feedback effect where faster winds generate more shock heating, which can affect the temperature structure and potentially accelerate the winds even further. The winds also transport chemical species around the planet, carrying vaporized metals from the day side, where they are created through evaporation to the night side, where they can condense. This transport is not instantaneous. It takes time for air parcels to travel from day side to night side. And during this transit, chemical reactions can occur. Thermal emission can cool the gas, and various physical processes can alter the composition and properties of the atmosphere. The timescale for global circulation, essentially the time it takes for air to travel from the subsolar point to the antistellar point. On the night side and back again, is probably measured in hours to a day or so, comparable to the planet's orbital period. This means atmospheric composition and temperature can vary significantly as material is carried around the planet by the winds. Observational evidence for these extreme winds comes from several sources. The thermal emission from KELT 9b varies over the course of its orbit in ways that suggest heat is being transported from the day side toward the night side by atmospheric circulation. Additionally, the point of maximum brightness, which would coincide with the subsolar point if there were no winds, appears to be offset slightly in the direction of the planet's motion around the star. This offset, called a hotspot offset, is a signature of winds carrying heat downwind from the subsolar point before it can be radiated away. By measuring this offset and combining it with theoretical models, scientists can estimate the wind speeds and circulation patterns, finding results consistent with the supersonic speeds predicted by theory. The winds on KELT 9b also affect the distribution of escaping atmosphere. Material that is being hydrodynamically stripped from the planet is not removed uniformly from all locations. Instead, the winds carry material to certain regions where conditions are more favorable for escape, potentially creating asymmetries in the extended atmosphere and the tail of escaping material. Some models suggest that most of the atmospheric escape might occur from the poles or from the night-side terminator regions where atmospheric dynamics concentrate material and where the geometry of the stellar wind interaction might enhance escape efficiency. Understanding these effects requires coupling models of atmospheric circulation with models of atmospheric escape, a challenging computational problem that pushes the limits of current simulation capabilities. The extreme winds also create fascinating scenarios when we imagine their effects. Any structure or feature in the atmosphere would be subjected to forces of incredible magnitude. If there were somehow clouds or atmospheric features analogous to Earth's thunderstorms, they would be ripped apart and dispersed by the supersonic winds in seconds. The concept of stable weather systems, as we know them, cannot apply on KELT 9b. Everything is transient, everything is in motion, and the violence of the atmospheric dynamics overwhelms any tendency toward stable structures. This is an atmosphere in constant turmoil, where change is the only constant, and where forces of nature operate at intensities that challenge our ability to model and comprehend them. Given all the extreme characteristics we have discussed, the eventual fate of KELT 9b is not one of peaceful stability extending billions of years into the future, but rather one of progressive destruction leading inevitably to the planet's complete annihilation. The planet is not in equilibrium with its environment. It is actively being dismantled by the very star it orbits, and multiple processes are conspiring to ensure that KELT 9b's remaining lifetime is geologically brief. Understanding the timeline and mechanism of the planet's doom requires examining several interconnected processes, each contributing to the planet's gradual but inevitable destruction. The most obvious destructive process is the atmospheric evaporation we have already discussed. KELT 9b is losing tens of thousands of metric tons of atmosphere per second, a rate of mass loss that, while small compared to the planet's total mass, adds up significantly over geological timescales. At current rates, the planet might lose a few Earth masses worth of material over 1 billion years. Not enough to destroy the entire planet, but enough to significantly change its properties. However, the mass loss rate itself may increase over time as conditions change, potentially accelerating the destruction. If the planet loses its outer hydrogen and helium envelope, the remaining core, if one exists, would be much more compact and would experience even more intense radiation, potentially leading to the vaporization of heavier materials. Beyond atmospheric evaporation, tidal effects are causing the planet to gradually spiral inward toward its star. The tides raised on KELT 9b by its star's gravity, and the tides raised on the star by the planet's gravity, dissipate energy as heat. This energy comes from the orbital energy of the system, causing the orbit to decay over time. For KELT 9b, already orbiting extremely close to its star, this inward migration will eventually bring it to a distance where tidal forces become stronger than the planet's self-gravity, a point called the Roche limit. When a planet crosses inside the Roche limit, it can no longer hold itself together and is torn apart by tidal forces, fragmenting into a ring of debris that gradually falls into the star. The timescale for this process depends on many factors, including the efficiency of tidal dissipation and the properties of both the planet and star. But estimates suggest KELT 9b might have only a few 100 million years remaining before it crosses the Roche limit. There is also the question of whether the star itself will change in ways that affect the planet's fate. KELT 9 is an A-type star, currently in the main sequence phase of its evolution, where it fuses hydrogen into helium in its core. However, A-type stars live fast and die young compared to cooler stars. KELT 9 probably has a total main sequence lifetime of only a few 100 million to perhaps 1 billion years before it exhausts the hydrogen in its core and begins to evolve off the main sequence. As stars evolve, they typically expand and increase in luminosity, which for KELT 9b would mean even more intense radiation and heating. The planet might not survive even to see its star leave the main sequence. It could be destroyed by tidal forces first. But if it somehow survives that long, the star's evolution would certainly doom it, either vaporizing it completely or engulfing it as the star expands. The combination of these factors paints a picture of a planet with very limited time remaining. Whether the planet is first destroyed by atmospheric evaporation removing its entire envelope, by tidal disruption tearing it apart, or by stellar evolution vaporizing it. The end result is the same. KELT 9b is doomed. This is not a world that will still exist in recognizable form a billion years from now. It might not even survive for a few 100 million years. The planet is caught in a cosmic death spiral from which there is no escape, a dramatic demonstration of the violent processes that can occur in planetary systems, and a reminder that planet formation and evolution are not always gentle processes leading to stable configurations like our solar system. There is something almost tragic about KELT 9b's fate when we anthropomorphize it. Here is a world that might have formed in a more benign location, perhaps a gas giant planet similar to Jupiter or Saturn in its early life, before something, likely gravitational interactions with other planets or the star itself during the planet's youth, caused it to migrate inward to its current deadly orbit. Over millions or perhaps billions of years, it has been subjected to increasingly hostile conditions, slowly losing its atmosphere, slowly spiraling inward, slowly being cooked by radiation that grows ever more intense. And eventually, whether in a dramatic tidal disruption event that tears the planet into fragments, or through gradual evaporation that slowly erodes it down to nothing, KELT 9b will cease to exist as a planet, its material dispersed into the space around the star, perhaps eventually falling into the star itself, or being blown away by stellar winds to drift through the galaxy as isolated atoms. All memory of the planet that once existed erased. The question of whether KELT 9b might leave behind any remnant after its destruction is interesting to contemplate. If the planet has a rocky core beneath its gaseous envelope, a remnant of the solid material that served as the seed for the planet's formation, this core might survive after the gaseous envelope is stripped away. Such a core would be subjected to even more intense radiation than the current planet's surface, likely causing it to vaporize as well. But there is a possibility that some ultra-refractory materials could persist. Alternatively, the planet might fragment during tidal disruption, creating multiple smaller bodies that briefly orbit the star before being destroyed themselves. Or perhaps the planet will be completely vaporized, leaving literally nothing behind except the atoms that once comprised it, now mixed into the stellar wind and interstellar medium. In contemplating KELT 9b's doom, we are also contemplating a process that has likely occurred countless times throughout the history of the galaxy. The universe is filled with systems where planets have been destroyed by their stars, where worlds have been vaporized or torn apart or flung out of their systems entirely. Most of these destruction events happen in the distant past or distant future, relative to our observations, so we don't see them occurring. But with KELT 9b, we are witnessing a destruction in progress, watching in real time as a planet is consumed by its environment. This makes KELT 9b not just scientifically interesting, but also cosmically significant. A window into processes that shape the architecture of planetary systems and determine which worlds survive and which are destroyed. To properly contextualize KELT 9b within the broader landscape of planetary science, we need to understand where it fits in the classification schemes astronomers use to categorize the bewildering diversity of planets discovered beyond our solar system. The discovery of thousands of exoplanets over the past few decades has revealed that planets come in many varieties that were never anticipated based solely on our solar system, and entirely new categories have been created to describe these unexpected worlds. KELT 9b falls into a specific category called ultra-hot Jupiters, planets that represent the absolute extreme end of planetary environments, and that challenge our understanding of planetary atmospheres formation, and evolution. The term hot Jupiter was coined in the 1990s after the discovery of the first exoplanets orbiting Sun-like stars, which surprisingly turned out to be gas giant planets, orbiting very close to their stars with orbital periods of only a few days. This was completely unexpected because, in our solar system, gas giants like Jupiter and Saturn orbit far from the Sun, taking years or decades to complete their orbits. The discovery of hot Jupiters revolutionized planetary science and led to the development of new theories of planetary migration, explaining how gas giants could form in the cold outer regions of planetary systems and then migrate inward to close orbits. Hot Jupiters are defined roughly as planets with masses similar to or greater than Jupiter that orbit their stars with periods of less than 10 days, placing them very close to their stars and heating them to temperatures ranging from around 1,000 Kelvin on the cooler examples up to 3,000 Kelvin or more on the hottest. Ultra-hot Jupiters represent a subset of hot Jupiters with even more extreme properties. While there is no universally agreed upon definition, most astronomers consider planets with dayside temperatures exceeding about 2,000 to 2,500 Kelvin to fall into this category. At these temperatures, the atmospheric chemistry and physics become qualitatively different from cooler hot Jupiters. Molecules begin to dissociate, atoms become ionized, and the atmospheres take on characteristics more similar to stellar atmospheres than to typical planetary atmospheres. As of current knowledge, several dozen ultra-hot Jupiters have been discovered, with names like WASP-12b, WASP-18b, WASP-121b, HAT-P7b, and WASP-76b becoming familiar to researchers in the field. Each of these worlds has its own extreme characteristics, from atmospheres with iron rain to planets so hot they glow like embers. Even among ultra-hot Jupiters, KELT 9b stands alone at the extreme end of the spectrum. With dayside temperatures of 4,600 Kelvin, it is significantly hotter than any other confirmed planet in this category. The next hottest planets have dayside temperatures around 3,500 to 4,000 Kelvin, still extraordinary but noticeably cooler than KELT 9b. This distinction is not just about setting records. The temperature difference represents a transition to even more extreme physical conditions. At 4,600 Kelvin, not only are all molecules dissociated, but ionization becomes significant. Atomic processes dominate, and the planet begins to behave more like a cool star than like a planet. KELT 9b has temperatures that overlap with the coolest red dwarf stars, blurring the line between planetary and stellar physics in a way that makes it uniquely valuable for understanding the limits of planetary environments. The classification of KELT 9b as an ultra-hot Jupiter also tells us something about its composition. Like Jupiter, KELT 9b is primarily composed of hydrogen and helium, the lightest and most abundant elements in the universe. But unlike Jupiter, where these elements exist as molecules and as metallic hydrogen deep in the interior, on KELT 9b, the hydrogen is at least partially atomic on the day side, and the helium, which is harder to ionize than hydrogen, remains mostly neutral, but at temperatures where it behaves very differently than in cooler environments. The planet probably also contains heavier elements mixed throughout its atmosphere and possibly concentrated in a core if one exists, though the extreme conditions make it difficult to determine the internal structure through observations. Understanding KELT 9b's place in planetary classification also involves comparing it to other types of extreme planets. Some planets, like Corot 7b and Kepler 10b, are rocky super-Earths orbiting so close to their stars that their surfaces are molten or even vaporized, creating lava worlds where rock behaves like water on Earth, evaporating and raining back down in a cycle of rock vapor weather. While fascinating, these worlds are much smaller than KELT 9b and lack the massive hydrogen atmospheres that characterize gas giants. Other planets like HD 189733 are known for having atmospheres with sideways rain made of glass particles traveling at thousands of kilometers per hour. Another extreme environment, but still cooler and less extreme than KELT 9b planets, like WASP 12b, are known to be spiraling into their stars even faster than KELT 9b, potentially being consumed within a few million years. Each of these worlds represents a different type of extreme environment, but KELT 9b combines multiple extremes into a single package, making it arguably the most comprehensively terrifying planet yet discovered. The study of ultra-hot Jupiters like KELT 9b has opened up new areas of research at the intersection of planetary science and stellar astrophysics. These planets serve as natural laboratories for studying matter under conditions that cannot be replicated in any laboratory on Earth. The temperatures and pressures present in their atmospheres allow scientists to test theories of atomic physics, thermodynamics, and radiation transfer under extreme conditions. The chemistry occurring in these atmospheres includes reactions and processes that may have been important in the early universe or in the atmospheres of stars, connecting planetary science to cosmology and stellar evolution in unexpected ways. Ultra-hot Jupiters have also driven the development of new observational techniques and instruments, as detecting and characterizing these extreme environments pushes the limits of current technology and motivates innovations in spectroscopy, photometry, and theoretical modeling. KELT 9b's classification as the most extreme ultra-hot Jupiter currently known does not mean it will remain alone at the top of the extremity scale forever. Surveys continue to discover new exoplanets, and it is possible that even hotter planets exist, waiting to be found around even hotter or more luminous stars, or orbiting even closer to their hosts. However, there are theoretical limits to how extreme a planet can be. If a planet orbits too close to its star, it will be tidally disrupted. If it is heated too intensely, it will lose its atmosphere so rapidly that it cannot maintain a gaseous envelope. If the star is too hot and massive, its lifetime might be so short that planets don't have time to migrate inward before the star evolves off the main sequence. KELT 9b may be approaching these theoretical limits, representing a planet at the absolute edge of what is possible in the universe. A world that barely qualifies as a planet, rather than a diffuse cloud of escaping gas. A final desperate configuration before the forces of nature overwhelm planetary structures entirely. One of the most puzzling aspects of KELT 9b, and of hot Jupiters and ultra-hot Jupiters in general, is the question of how these planets came to exist in their current configurations. The formation mystery surrounding these worlds represents one of the major unsolved problems in planetary science and has driven decades of theoretical work attempting to explain the origin of such unexpected systems. To understand the mystery, we must first understand what theories of planet formation predicted before the discovery of hot Jupiters, and then grapple with how dramatically observations have forced revisions to those theories. Traditional theories of planet formation, developed largely from observations of our own solar system, suggested that gas giant planets like Jupiter and Saturn form in the cold outer regions of protoplanetary disks beyond what is called the snow line or ice line, the distance from the star where temperatures are low enough for water and other volatiles to condense into ice. In the warm inner regions of protoplanetary disks, close to the star, only rocky and metallic materials can remain solid. leading to the formation of small rocky planets like Earth and Mars. But beyond the snowline, ice can exist, dramatically increasing the amount of solid material available. Small, icy and rocky grains collide and stick together, gradually growing into larger bodies called planetesimals. When a planetesimal grows to about 10 times Earth's mass, it develops strong enough gravity to begin capturing gas directly from the surrounding disk, and a runaway process begins where more mass attracts more gas, leading to the rapid formation of a gas giant planet. This theory explained the architecture of our solar system beautifully, with small rocky planets close to the Sun and large gas giants farther out. It also made sense from a chemical and thermodynamic perspective, as the high temperatures close to young stars would prevent ice from existing and would make it difficult for planets to accumulate the enormous masses of hydrogen and helium needed to become gas giants. When the first exoplanets were discovered in the 1990s, astronomers expected to find systems similar to our own, with gas giants, if present, orbiting far from their stars. Instead, they found gas giant planets orbiting their stars every few days, planets that came to be called hot Jupiters, located in regions where the theory said they should not be able to form. This discrepancy forced a revolution in thinking about planet formation and evolution. The consensus that emerged was that hot Jupiters must have formed farther from their stars, beyond the snowline where conditions were favorable for gas giant formation, and then migrated inward to their current locations through some combination of gravitational interactions and physical processes. Several mechanisms for this migration have been proposed and studied in detail. One mechanism involves interactions between the young planet and the protoplanetary disk of gas and dust from which it formed. As a planet orbits within a disk, it creates gravitational disturbances that propagate through the disk, removing angular momentum from the planet's orbit and causing it to gradually spiral inward toward the star. This process, called Type 1 or Type Tab migration, depending on the planet's mass and the disk conditions, can move planets substantial distances over timescales of thousands to millions of years. Another proposed mechanism involves gravitational interactions between multiple planets in a system. If two or more giant planets form in the same system, they can gravitationally perturb each other's orbits, potentially placing one planet on a highly elliptical orbit that brings it very close to the star at its closest approach. Tidal forces. During these close approaches, gradually circularize the orbit, leaving the planet in a close circular orbit. This process might also involve ejecting one planet from the system entirely, using the recoil from that ejection to push another planet inward. Yet another mechanism involves the Kozai leadoff effect, where a distant companion star or massive planet on an inclined orbit can cause periodic oscillations in another planet's orbit, sometimes bringing it very close to the star before tidal forces circularize the orbit at small distance. For KELT 9b specifically, the formation history remains unclear. The planet orbits a relatively young, massive, and hot star, which has implications for how long the protoplanetary disk would have persisted and what conditions would have been like during the planet formation. Epoch A-type stars like KELT 9 disperse their protoplanetary disks more rapidly than cooler stars like our Sun, because their intense radiation and stellar winds blow away the gas more quickly. This means that if disk migration was responsible for moving KELT 9b inward, the process must have occurred quickly, within perhaps a few million years after the planet formed. The rapid orbital decay timescales and the short disk lifetimes around hot stars create a narrow window for migration to occur. making the formation of ultra-hot Jupiters around A-type stars particularly challenging to explain. Another complication for KELT 9b's formation involves the extreme conditions the planet now experiences. If the planet migrated to its current location billions of years ago, it has been subjected to intense stellar radiation for most of its lifetime, slowly losing its atmosphere throughout that entire period. The planet might have been significantly more massive when it first arrived in its current orbit, with perhaps many times more atmospheric mass than it currently possesses. Alternatively, the planet might have migrated inward relatively recently, perhaps only a few 100 million years ago, and most of the atmospheric loss has occurred recently. Distinguishing between these scenarios requires understanding the rates of atmospheric escape and migration, both of which are difficult to constrain precisely. Some researchers have even proposed that certain hot Jupiters, possibly including extremely hot ones like KELT 9b, might represent failed stars that never accumulated enough mass to ignite fusion in their cores. These objects, called brown dwarfs when they are more massive than about 13 Jupiter masses, can exist at masses just below or around the planetary threshold. If KELT 9b formed through the same gravitational collapse process that formed stars, just on a smaller scale, its current location close to KELT 9 might not require complex migration scenarios. However, the planet's mass of about 3 Jupiter masses places it well below the brown dwarf regime, making this scenario less likely for KELT 9b specifically, though the boundary between massive planets and brown dwarfs remains somewhat fuzzy and definitionally complex. The composition of KELT 9b provides some clues about its formation, but also raises additional questions. The planet's density suggests it is primarily composed of hydrogen and helium, consistent with formation as a gas giant planet. However, the presence of heavy elements in the atmosphere, including the vaporized metals we discussed earlier, indicates that the planet either formed with a significant amount of heavy elements mixed throughout, or that it has a substantial core of rocky and metallic material that is contributing volatiles to the atmosphere through evaporation. The metallicity of the atmosphere, the abundance of elements heavier than helium, can provide information about where in the protoplanetary disk the planet formed and what materials were available during formation. Though measuring precise abundances in such extreme conditions is challenging. The formation mystery extends beyond just explaining how KELT 9b arrived at its current location to asking how any gas giant planet can survive such extreme conditions. When a planet migrates very close to its star, the stellar radiation begins to heat and strip away its atmosphere. For many planets, this atmospheric loss would remove the gaseous envelope entirely, leaving only a rocky core behind. That KELT 9b has survived with a substantial atmosphere suggests either that the migration occurred relatively recently on geological timescales, that the planet formed with such a large atmospheric mass that even rapid mass loss hasn't depleted it yet, or that the planet somehow continues to retain enough atmosphere through its gravity despite the intense escape processes. Understanding which of these scenarios applies to KELT 9b requires detailed modeling of atmospheric escape coupled with models of orbital migration and tidal evolution. The broader population of hot Jupiters and ultra-hot Jupiters provides additional context for understanding KELT 9b's formation. Observations show that hot Jupiters are relatively rare, occurring around only about 1% of Sun-like stars, suggesting that the conditions necessary for their formation and migration are not commonly met. Ultra-hot Jupiters are even rarer, comprising perhaps only 10 to 20% of the hot Jupiter population. This rarity might reflect the difficulty of migrating planets to such extreme locations, or It might reflect the rapid destruction of planets that do reach such orbits, creating a selection effect where we observe only the youngest or most massive survivors. KELT 9b, as the most extreme example yet found, might represent the absolute peak of a distribution of planetary outcomes. A 1 in a million combination of circumstances that created a world at the furthest possible extreme of planetary environments. Despite the uncertainties, studying systems like KELT 9b is gradually allowing astronomers to piece together the story of how these extreme planets form and evolve. By comparing the properties of many hot and ultra-hot Jupiters, looking for patterns in their masses, orbital periods, atmospheric compositions, and the properties of their host stars, researchers can test different formation scenarios and rule out mechanisms that are inconsistent with observations. Each new ultra-hot Jupiter discovered adds another data point to this puzzle, and each detailed characterization of planets like KELT 9b provides constraints on theoretical models. Over time, a clearer picture is emerging of the violent and chaotic processes that shape planetary systems. Processes far more dramatic and varied than the relatively orderly formation of our own solar system might suggest. The tools and techniques that astronomers use to study a planet as distant and extreme as KELT 9b represent some of the most sophisticated technologies and methodologies in modern astronomy. Spectroscopic analysis, the primary method for determining the composition and properties of the planet's atmosphere, relies on fundamental physics and cutting-edge instrumentation working together to extract information from the faint light that reaches Earth after passing through or being emitted by the planet's atmosphere. Understanding these techniques illuminates both the impressive capabilities of contemporary astronomy and the significant challenges that remain in characterizing distant worlds. The foundation of spectroscopic analysis is the principle that different chemical elements and compounds interact with light in characteristic ways. Each element has a unique set of energy levels that its electrons can occupy, and when an atom absorbs a photon of light, an electron jumps from a lower energy level to a higher one. Only photons with exactly the right energy can cause this transition. And because photon energy is directly related to wavelength, each element absorbs light at specific wavelengths. When we spread light out into a spectrum, displaying intensity as a function of wavelength, we see dark absorption lines at the wavelengths where photons have been removed by absorption. By identifying which wavelengths show absorption, we can determine which elements are present in the material the light passed through. For KELT 9b, the primary technique is called transit spectroscopy. When the planet passes in front of its star from our perspective, a small fraction of the starlight passes through the planet's atmosphere on its way to Earth. Atoms and molecules in the atmosphere absorb light at their characteristic wavelengths, imprinting absorption features on the stellar spectrum. By comparing the spectrum of the star when the planet is transiting with the spectrum, when the planet is not transiting, astronomers can isolate the absorption features caused by the planet's atmosphere. This requires extremely precise measurements because the atmosphere of even a giant planet like KELT 9b blocks only a tiny additional fraction of the star's light beyond what the planet's solid body blocks, typically much less than 1% additional blocking even at the strongest absorption wavelengths. The challenges involved in transit spectroscopy of KELT 9b are formidable. First, the star is very bright and hot, with a spectrum that peaks in the ultraviolet and blue regions rather than in the redder wavelengths, where cooler stars emit most of their light. This means observations must be conducted carefully to avoid saturating detectors or introducing systematic errors. Second, the planet transits only once every 36 hours, and each transit lasts only a few hours. providing a limited window for observations. Missing a transit means waiting another day and a half for the next opportunity. Third, the spectroscopic signals are extremely subtle, requiring instruments with very high precision and stability. Any instrumental variations, atmospheric effects from Earth's own atmosphere or other sources of noise can easily overwhelm the tiny signals being sought. To overcome these challenges, astronomers use the largest and most sophisticated telescopes available, equipped with specially designed spectrographs that can achieve the necessary precision. Ground-based telescopes like the Very Large Telescope in Chile, equipped with instruments like espresso and UVES, have been used to obtain high-resolution spectra of KELT 9b during transits. Space-based observatories like the Hubble Space Telescope, which observes from above Earth's atmosphere and avoids atmospheric distortions, have also observed the system. More recently, the James Webb Space Telescope, with its unprecedented sensitivity in the infrared, has begun observing ultra-hot Jupiters, though KELT 9b's extreme temperature means it emits more strongly in the visible and near-infrared than in the longer wavelengths where Webb is optimized. High-resolution spectroscopy, which spreads light out into very finely detailed spectra, allows astronomers to detect individual absorption lines from specific atoms. This technique was crucial for detecting the vaporized metals in KELT 9b's atmosphere, as each metal has a unique pattern of absorption lines that serves as a fingerprint. By cross-correlating observed spectra with theoretical templates showing where different atoms should absorb, researchers can detect the presence of even minor atmospheric constituents and can sometimes measure the velocities of atmospheric winds through Doppler shifts of the absorption lines. This technique has revealed not just what elements are present in KELT 9b's atmosphere, but also how those elements are distributed and how fast the atmosphere is moving. Emission spectroscopy provides another tool for studying KELT 9b. Because the planet is so hot, it emits substantial thermal radiation of its own, particularly in the infrared. When the planet is visible in our view, just before or after it passes behind the star, we receive light that is the sum of reflected starlight and thermally emitted light from the planet. When the planet goes behind the star in an event called a secondary eclipse, the planet's light is blocked and we see only the star. By comparing observations with the planet visible to observations during secondary eclipse, astronomers can isolate the planet's emission spectrum. This reveals information about the temperature structure of the atmosphere and about which atoms and molecules are emitting radiation. The analysis of spectroscopic data from KELT 9b involves sophisticated modeling and statistical techniques. Researchers must account for the complex geometry of the observation, including how the line of sight through the planet's atmosphere changes during transit, how the atmosphere's temperature and pressure vary with altitude, and how different atmospheric constituents are distributed. They must also account for the star's spectrum and any variability in stellar properties, the effects of the instrument itself, and various other factors. The process typically involves creating theoretical models of the atmosphere, computing what spectrum those models would produce, and then adjusting model parameters to find the best match to the observed data. This requires substantial computational resources and expertise in radiative transfer, atmospheric physics, and data analysis. Recent advances in technology and technique continue to improve our ability to characterize KELT 9b and similar planets. New instruments being developed for extremely large telescopes currently under construction will offer even greater sensitivity and spectral resolution. Machine learning algorithms are being applied to help extract subtle signals from noisy data. Improved theoretical models of atmospheric chemistry and physics under extreme conditions allow more accurate interpretation of observations. Each improvement brings us closer to a complete understanding of what KELT 9b is really like, transforming it from an abstract set of numbers and inferred properties into a vivid picture of an actual place, albeit a place so hostile that no human could ever visit it or survive anywhere near it. The spectroscopic analysis of KELT 9b also demonstrates the power of modern astronomy to study places that are literally beyond our reach by any conceivable spacecraft technology. The planet is 670 light-years away, a distance so vast that even signals traveling at the speed of light take more than 6 centuries to cover it. Yet through careful analysis of the light that has made that journey, we can determine what atoms are present in the atmosphere, estimate the temperature, measure the wind speeds, and track how the planet is losing its atmosphere to space. This represents a triumph of scientific methodology, using fundamental physics and mathematics, combined with advanced technology to extract information from minimal data, building knowledge about the universe through observation and reasoning. The atmospheric chemistry occurring on KELT 9b operates in a regime that has rarely been studied in any context, terrestrial or astronomical, creating opportunities to observe chemical processes and reactions that cannot be replicated in laboratories on Earth, and that provide insights into fundamental physics and chemistry under extreme conditions. Understanding this chemistry requires combining knowledge from multiple scientific disciplines, including atomic physics, thermodynamics, fluid dynamics, and radiation transfer, creating a complex picture of a world where the usual rules of atmospheric chemistry do not apply, and where new phenomena emerge from the extreme environment. At the most basic level, the chemistry of KELT 9b is dominated by dissociation and recombination reactions. On the day side, molecules are torn apart by thermal energy, creating a soup of individual atoms. The rate at which molecules dissociate depends on temperature, according to well-established physical principles described by equations like the Saha equation, which predicts the degree of ionization and dissociation as a function of temperature, pressure, and composition. At 4,600 Kelvin, essentially all molecules with dissociation energies less than about 6 electron volts are completely dissociated. This includes water, carbon dioxide, methane, ammonia, and even molecular hydrogen, which has a relatively high dissociation energy of about 4.5 electron volts. The dissociation process is not instantaneous, but occurs through collisions between molecules and other particles. At the high temperatures present on KELT 9b, particles move at average speeds of several kilometers per second, and collisions are frequent and energetic. When two molecules collide with sufficient energy, the impact can break molecular bonds, separating the atoms. Similarly, photons from the star with energies exceeding the molecular bond. Energy can cause photodissociation, where absorption of a photon directly breaks a molecule apart. Both thermal dissociation and photodissociation contribute to the destruction of molecules on KELT 9b's dayside, ensuring that molecular species cannot persist in the hottest regions. Once atoms are liberated from molecules, they can undergo further reactions. Ionization becomes important at the highest temperatures and in regions exposed to the most intense ultraviolet radiation. Ionization removes electrons from atoms, creating positively charged ions and free electrons. The ionization energy, the energy required to remove an electron, varies by element. Hydrogen has an ionization energy of about 13.6 electron volts, meaning temperatures of around 160,000, Kelvin would be needed to thermally ionize a substantial fraction of hydrogen atoms. The temperatures on KELT 9b are not high enough for significant thermal ionization of hydrogen. But photoionization by high-energy ultraviolet photons from the star can remove electrons, creating a partially ionized component to the atmosphere. Heavier atoms have a wider range of ionization energies, with alkali metals like sodium and potassium being relatively easy to ionize, while noble gases like helium are very difficult to ionize. The presence of ions in the atmosphere affects its properties significantly. Ions interact much more strongly with magnetic fields than neutral atoms do. So regions with significant ionization can be strongly influenced by the stellar magnetic field and can experience forces that neutral gas would not feel. Ions also change the electrical conductivity of the atmosphere, potentially allowing electric currents to flow and creating complex electromagnetic phenomena. As atmospheric gas moves from the hot day side toward the cooler night side, the chemistry reverses. Atoms begin to recombine into molecules as temperatures drop below the dissociation threshold for various species. The formation of molecules from atoms releases energy, the reverse of the energy that was absorbed during dissociation. For hydrogen, two hydrogen atoms combining to form an H2 molecule releases about 4.5 electron volts of energy. This energy heats the local gas, contributing to the overall energy budget of the atmosphere and affecting the temperature structure. The recombination process is not instantaneous. It requires collisions between atoms with the right energies and geometries, and the rates depend on temperature, pressure, and the presence of third bodies that can carry away excess energy. The chemistry of metals in the atmosphere adds additional complexity. As we discussed, metals like iron, magnesium, and others are vaporized on the day side and can condense on the night side. But the condensation process itself involves intricate chemistry. Metal atoms must first cluster together, forming small aggregates or embryonic particles. These clusters then grow through accretion of additional atoms, eventually forming particles large enough to be considered cloud droplets. The details of this nucleation and growth process depend on thermodynamic properties like surface tension, supersaturation ratios, and the presence of seed particles. Some models suggest that refractory compounds like calcium aluminum-rich inclusions, similar to the first solid particles that formed in our own solar system's protoplanetary disk, might serve as condensation nuclei for metal clouds. The chemical reactions involving metals can also produce molecular species not seen elsewhere in planetary atmospheres. Titanium oxide and vanadium oxide, for instance, are molecules that form in cool stellar atmospheres and can potentially form in the cooler regions of KELT 9b's atmosphere. These molecules have complex optical properties and can strongly absorb visible and ultraviolet light, affecting the atmosphere's thermal structure. The formation and destruction of these molecules creates additional pathways for chemical reactions, and their presence or absence can significantly influence atmospheric properties. Detecting these species through spectroscopy helps constrain models of atmospheric temperature and circulation. Another fascinating aspect of KELT 9b's chemistry involves the potential for non-equilibrium processes. In chemical equilibrium, the rates of forward and reverse reactions balance, and the composition remains stable over time. But on KELT 9b, the rapid transport of gas between hot and cold regions by supersonic winds means that gas parcels don't remain at any particular temperature long enough to reach equilibrium. Material might be carried from the hot day side to the cooler night side, faster than chemical reactions can adjust the composition to match the new temperature, creating disequilibrium chemistry where the atmospheric composition reflects the history of the gas parcel, rather than just its current temperature. Understanding these disequilibrium effects requires modeling the coupling between atmospheric dynamics and chemistry, tracking how composition evolves as gas moves around the planet. The extreme chemistry on KELT 9b also provides a laboratory for studying atomic and molecular physics in regimes that are difficult to access experimentally. The temperatures and pressures present in the atmosphere allow collisions and reactions that require significant activation energies, processes that might be too slow or unlikely at lower temperatures. By observing which species are present and which are absent in the atmosphere, and by measuring reaction rates through time-resolved observations, astronomers can test theoretical predictions from quantum chemistry and atomic physics. In some cases, uncertainties in fundamental atomic data, like transition probabilities or dissociation energies, limit the accuracy of atmospheric models, and observations of planets like KELT 9b can help refine these fundamental parameters. The chemistry of escaping atmospheric material presents yet another frontier. As gas escapes hydrodynamically from the planet, it passes through regions of progressively lower density and higher radiation intensity. In these regions, chemical processes may differ from those deeper in the atmosphere. Photochemistry, driven by stellar ultraviolet radiation, becomes dominant, potentially creating exotic species through photodissociation and photoionization processes. The escaping material also interacts with the stellar wind, the stream of charged particles flowing outward from the star, creating a complex boundary region where planetary and stellar materials mix and interact. Understanding the chemistry in this extended envelope and tail of escaping material requires models that bridge the gap between atmospheric chemistry and space plasma physics. To place KELT 9b in proper perspective and truly appreciate its extremity, we must compare it to other planets known for their own horrific characteristics, creating a cosmic rogues gallery of the worst worlds in the universe. This comparison reveals both what makes KELT 9b unique and what features it shares with other hellish worlds, providing context for understanding the diversity of hostile environments that exist among exoplanets. While KELT 9b claims the title of hottest confirmed planet, other worlds compete in different categories of terror, each offering its own brand of cosmic horror. WASP-12b, located about 1400 light-years from Earth, represents one of the closest analogues to KELT 9b in terms of extreme conditions, with dayside temperatures around 2800 Kelvin, considerably cooler than KELT 9b, but still hot enough to melt most metals. WASP-12b orbits even closer to its star than KELT 9b does, relative to the sizes of their respective stars. The planet is being tidally distorted into an egg shape by the intense gravitational forces, and it is losing mass even faster than KELT 9b, with estimates suggesting it might be completely destroyed within a few million years, far faster than KELT 9b's destruction timescale. Observations have detected carbon monoxide and water vapor in its atmosphere, though these molecules can only exist in cooler regions. WASP-12b was one of the first planets where atmospheric escape was detected, making it a prototype for understanding how planets are destroyed by their stars. HD 189733b, about 63 light-years away, is famous for different reasons. While cooler than KELT 9b with dayside temperatures around 1300 Kelvin, this planet experiences winds exceeding 8,000 kilometers per hour, faster even than KELT 9b's supersonic winds in absolute velocity. The planet is a striking cobalt blue color, but not for pleasant reasons. The color comes from silicate particles in the atmosphere, tiny grains of glass-like material that form clouds and are whipped around by the intense winds. This creates conditions where it quite literally rains molten glass sideways at speeds that would shred any object exposed to them. The planet also experiences intense stellar flares from its highly active host star, bombarding the atmosphere with X-rays and ultraviolet radiation that may be slowly stripping away the atmosphere. CoRo T7b, about 490 light-years distant, represents a different category of hellish world entirely. This is a rocky super-Earth, not a gas giant, with a mass only about 5 times Earth's mass. But it orbits so close to its star that its day side is heated to around 2,600 Kelvin, hot enough that the surface rocks are molten or even vaporized. The planet likely has an atmosphere composed of vaporized rock, with compounds like silicate vapor, sodium, and potassium floating in the air above a magma ocean. At night, these rock vapors condense and fall as rock rain, perhaps creating pebbles that pile up on the night side before being vaporized again, when carried back to the day side by lava flows. This creates a terrifying vision of a world where weather consists of raining rocks and where the surface itself is liquid rather than solid. WASP-76b, roughly 390 light-years away, has become famous for iron rain. With dayside temperatures around 2,400 Kelvin, hot enough to vaporize iron, and nightside temperatures cool enough for iron to condense, the planet experiences an iron cycle similar to Earth's water cycle. Iron evaporates on the hot day side, is carried by winds to the night side, where it condenses into clouds and rain, and presumably collects as molten iron lakes or oceans on the night side, before being recirculated. Observations have detected strong asymmetries in iron absorption between the morning and evening sides of the planet, consistent with iron condensing on the cooler evening side after being vaporized on the day side. WASP-121b, about 880 light-years distant, has dayside temperatures around 2,500 to 3,000 Kelvin, making it one of the hotter planets known besides KELT 9b. It is notable for having an extremely inflated atmosphere, with a radius nearly twice Jupiter's radius, despite having a similar mass, giving it an extremely low average density. The atmosphere is so hot and extended that it is escaping rapidly into space, and observations have detected gaseous metals, including magnesium and iron. The planet's atmosphere may contain stratosphere, a layer where temperature increases with altitude, something predicted to occur when metals and metal oxides in the atmosphere absorb stellar radiation and heat the upper atmosphere. Kepler-10b is another super-Earth with horrific conditions. Orbiting extremely close to its star with a period of only 20 hours, its day side reaches temperatures around 2,000 Kelvin. The planet is thought to be rocky with an iron-rich composition, and models suggest the surface could be molten on the day side. Some researchers have speculated about lava flows on the surface, transporting heat from day side to night side, creating a dynamic surface more similar to Io, Jupiter's volcanically active moon, than to the stable surface of Earth. When we compare all these extreme worlds to KELT 9b, patterns emerge. Many ultra-hot planets are experiencing rapid mass loss and face destruction on relatively short timescales. Many show evidence of vaporized metals in their atmospheres. Many are tidally locked with extreme day-night temperature contrasts. But KELT 9b combines the highest temperatures, substantial size maintaining a significant atmosphere despite rapid escape, and orbital characteristics that place it at the absolute limit of planetary survival. Where other planets might be hotter than some stars at specific wavelengths or have specific extreme characteristics, KELT 9b is hotter than billions of actual stars in absolute temperature terms and combines multiple extremes into a single world. The diversity among these extreme planets also tells us something about the range of conditions under which planets can exist and the various pathways to planetary destruction. Some planets are destroyed primarily by tidal forces, others primarily by atmospheric escape, others through impacts or ejection from their systems. Some experienced their extreme conditions only recently after migrating inward, while others have been in hellish orbits for billions of years. Each planet's story is unique, shaped by the particular combination of stellar properties, planetary mass and composition, orbital characteristics, and evolutionary history that defines its existence. KELT 9b's distinction as the most terrifying planet, then, comes not from dominating every category of extremity, but from the combination and intensity of extreme characteristics it possesses. It achieves the highest confirmed temperature of any planet, placing it in a category that overlaps with stellar physics, rather than planetary science. It orbits one of the hottest and most massive stars known to host planets, subjecting it to radiation environments beyond what most other planets experience. It is losing its atmosphere catastrophically, yet maintains substantial mass, creating a dramatic ongoing process we can observe in real time. And it faces certain doom on timescales that are short by cosmic standards, making it a planet in its final death throes rather than a stable world that might persist for billions of years. To fully appreciate the alienness and hostility of KELT 9b, we can engage in thought experiments exploring what would happen to various materials, objects, or even hypothetical spacecraft if they could somehow approach this world. These what-if scenarios help make the abstract numbers describing KELT 9b's temperature and environment more concrete by connecting them to things we can visualize and understand from everyday experience. The results paint a picture of destruction so complete and rapid that it challenges our intuitive understanding of heat and vaporization. Imagine attempting to place a block of iron, one of the strongest and most heat-resistant common materials, in orbit around KELT 9b at the same distance as the planet's surface. From its star, iron melts at about 1511 Kelvin and boils at about 3134 Kelvin. Within minutes or perhaps seconds of exposure to the 4600 Kelvin environment on KELT 9b's day side, the iron would not just melt but boil, vaporizing completely into a cloud of iron atoms that would quickly be swept away by the stellar wind and atmospheric flows. There would be no gradual heating, no time to observe the melting process. The iron would transition nearly instantaneously from solid to vapor, skipping the liquid phase entirely in many regions where the temperature exceeds the boiling point. Consider what would happen to more exotic materials. Tungsten, the metal with the highest melting point of any element at 3695 Kelvin, would fare slightly better than iron, but only marginally. It would remain solid for a brief period, but would quickly reach its melting point, and then exceed its boiling point at about 5930 Kelvin. Even tungsten, used in applications specifically because of its extreme heat resistance, cannot survive the environment of KELT 9b's dayside. The only materials that might persist as solids, at least briefly, are certain exotic compounds with extremely high sublimation temperatures, and even these would not survive long-term exposure. Diamond, one of the hardest substances known and composed of carbon in an extremely stable crystal structure, provides another interesting case: carbon sublimates, transitioning directly from solid to gas without passing through a liquid phase. At temperatures around 3800, Kelvin at atmospheric pressure. On KELT 9b, a diamond would begin to sublimate almost immediately upon exposure to the dayside environment, slowly eroding as carbon atoms break free from the crystal lattice and become part of the atmosphere. Within hours or days, depending on its size, the diamond would be completely consumed, its atoms distributed throughout the planet's atmosphere, or even escaping into space as part of the hydrodynamic outflow. Now, imagine trying to send a spacecraft to observe KELT 9b up close. Current spacecraft use heat shields and thermal protection systems to survive entry into planetary atmospheres or close approaches to the Sun. The Parker Solar Probe, humanity's closest solar approach mission, will pass within about 6 million kilometers of the Sun's surface, experiencing temperatures around 1400 Kelvin on its heat shield. To survive this, it uses a thick carbon composite heat shield and careful orientation to keep sensitive instruments in shadow. But KELT 9b's environment is 3 times hotter than what Parker Solar Probe's heat shield can withstand, and that's not even considering the intense ultraviolet radiation and the stellar wind from KELT 9. A hypothetical spacecraft attempting to approach KELT 9b at the planet's orbital distance would face insurmountable challenges. At several million kilometers away, the radiation flux from KELT 9 alone would begin heating any exposed surfaces to hundreds of degrees. As the spacecraft approached closer, temperatures would climb rapidly. By the time it reached KELT 9b's orbital distance, any conventional materials would be vaporizing. Electronics would fail long before reaching such temperatures, as most electronic components cannot operate above a few hundred Kelvin. Even if we imagined some exotic future technology with heat-resistant components, the sheer intensity of the radiation would overwhelm any cooling system. The spacecraft would need to radiate away tens or hundreds of kilowatts per square meter of absorbed energy, an impossible task for any realistic thermal management system. Water, the substance that covers most of Earth's surface and is essential to all known life, would fare terribly on KELT 9b. Water molecules, as we have discussed, are completely dissociated into hydrogen and oxygen atoms on the day side. But even on the night side, where temperatures might allow water molecules to briefly exist, liquid water is impossible. The triple point of water, the unique temperature and pressure where solid, liquid, and gas phases can coexist, is at about 273 Kelvin and 612 pascals. Above the critical point at about 647 Kelvin and 22 megapascals, water cannot exist as a distinct liquid phase at any pressure. The temperatures everywhere on KELT 9b far exceed these values, meaning water can only exist as either individual atoms or, in the very coolest regions, briefly as molecules in gas phase. Biological materials would be destroyed instantly and completely. Proteins, the molecular machines that perform most functions in living cells, denature and break down at temperatures above about 340 Kelvin. For most types' DNA, the genetic material that encodes information for life begins to break down at similar temperatures, with the hydrogen bonds holding the double helix together, breaking apart well below 400 Kelvin. On KELT 9b, any biological molecules would not just denature, but would be completely decomposed into their constituent atoms. The carbon, hydrogen, nitrogen, oxygen, and other elements that make up living organisms would be separated and distributed throughout the atmosphere, making any form of life as we know it absolutely impossible. Even hypothetical silicon-based life forms, sometimes proposed as alternatives to carbon-based biochemistry that might function at higher temperatures, could not survive on KELT 9b silicon-silicon bonds. While more thermally stable than some carbon bonds, still break down well below the temperatures on KELT 9b. Any conceivable biochemistry requires molecules to maintain stable structures and undergo controlled reactions, and molecular stability is impossible at 4600 Kelvin. KELT 9b is not just hostile to life, it is hostile to chemistry itself in the traditional sense, existing in a regime where atomic physics dominates over molecular chemistry. These thought experiments reveal that KELT 9b exists in a category of its own, a place where our intuitive understanding of materials and their properties breaks down completely. This is a world where everything we consider durable vaporizes, where temperatures exceed the operating ranges of any conceivable technology, and where the very concept of a solid surface becomes questionable for a gas giant planet whose atmosphere is hot enough to behave more like a stellar atmosphere than a planetary one. The impossibility of approaching or surviving near KELT 9b makes it, in a very real sense, more alien and inaccessible than almost any other place in the universe. We could, in principle, imagine sending spacecraft to the surfaces of neutron stars, or into black hole accretion disks in the far future with sufficiently advanced technology. But KELT 9b's environment is hostile in such a comprehensive way that even science fiction struggles to imagine a scenario where humans or our machines could study it up close. The scientific significance of KELT 9b extends far beyond its status as a cosmic curiosity or record holder for extreme conditions. The planet serves as a natural laboratory for testing theories and models that would be impossible to validate through any other means, providing insights that ripple across multiple fields of astronomy and physics. Understanding why studying KELT 9b matters requires examining the fundamental questions that drive modern planetary science, and how this extreme world helps answer them. One major area where KELT 9b provides crucial insights is in understanding stellar evolution and the interactions between stars and planets. A-type stars like KELT 9 are relatively poorly understood compared to Sun-like stars, in part because their higher masses and temperatures make them evolve more rapidly and make their planetary systems more difficult to study. By observing how KELT 9b's atmosphere responds to the intense stellar radiation, astronomers can learn about the properties of the radiation field around A-type stars, including the intensity of ultraviolet emission, the stellar wind properties, and the variability of stellar activity. This information feeds back into models of stellar physics, improving our understanding of how massive stars evolve and how they affect their environments. The study of atmospheric escape processes on KELT 9b provides insights relevant to understanding planetary atmospheres throughout the universe. Atmospheric escape is a fundamental process that affects all planets to varying degrees. Earth slowly loses hydrogen from the top of its atmosphere. Mars lost most of its atmosphere over billions of years through escape processes. Venus has a different history of atmospheric loss and gain. By observing atmospheric escape on KELT 9b, where it occurs at extreme rates and can be measured relatively easily, scientists can test models of hydrodynamic escape, photoevaporation, and other mechanisms. These models, once validated against observations of KELT 9b, can be applied to other planets with greater confidence, helping us understand the long-term evolution of planetary atmospheres in our solar system and around other stars. KELT 9b also helps us understand the limits of planet formation and the diversity of planetary system architectures. The existence of planets like KELT 9b, orbiting so close to such hot stars, challenges theories of planet formation and migration. By studying many ultra-hot Jupiters and understanding what fraction of stars host such planets, what stellar properties correlate with their presence, and what planetary properties characterize the population, astronomers constrain the physical processes involved in planet formation. Every discovery of a planet like KELT 9b that theory struggles to explain forces refinements to the models, gradually improving our understanding of how planetary systems form and evolve. The atmospheric chemistry of KELT 9b provides a laboratory for studying high-temperature chemistry under conditions that cannot be replicated on Earth. The most advanced laboratory furnaces and plasma chambers can achieve high temperatures, but they operate at pressures and compositions very different from planetary atmospheres, and they cannot sustain conditions over the large scales and long timescales present in planetary atmospheres. By observing which chemical species are present in KELT 9b's atmosphere and measuring their abundances, scientists can test theoretical models of chemical equilibrium and kinetics at extreme temperatures. The data from KELT 9b helps refine fundamental chemical constants like reaction rates, bond energies, and thermodynamic properties that are used across many fields of science and engineering. The study of KELT 9b also advances observational techniques and technologies in ways that benefit all of astronomy. The challenges of detecting and characterizing such an extreme planet have driven the development of new spectroscopic methods, more sensitive instruments, and more sophisticated data analysis algorithms. These tools, once developed for studying ultra-hot Jupiters, can be applied to studying other types of planets, stars, and astronomical phenomena. The push to understand KELT 9b motivates investments in larger telescopes, better detectors, and improved theoretical models that serve the entire astronomical community. In this sense, KELT 9b serves as a technological driver, pushing the boundaries of what is observationally possible. From a philosophical and broader scientific perspective, KELT 9b challenges our assumptions about what a planet can be and expands our conception of the diversity of worlds in the universe. Before the discovery of exoplanets, our entire understanding of planetary science was based on 8 examples in our solar system, plus their moons and minor bodies. This limited sample suggested certain patterns: rocky planets close to stars, gas giants farther out, relatively circular orbits, and conditions varying from cold to temperate. The discovery of hot Jupiters, super-Earths, ice giants, lava worlds, and ultra-hot Jupiters like KELT 9b has shattered these preconceptions, revealing that our solar system is just one possibility among many, and perhaps not even a particularly common one. KELT 9b specifically shows us that planets can exist in conditions that seem fundamentally hostile to planetary survival. The traditional definition of a planet as a body in hydrostatic equilibrium, orbiting a star, and having cleared its orbit becomes almost quaint when applied to a world like KELT 9b, which is barely holding itself together against the forces trying to tear it apart. The planet exists in a liminal state between planetary and stellar physics, between bound atmosphere and escaping gas cloud, between stable configuration and catastrophic disruption. Studying KELT 9b forces us to think carefully about what we mean by planet and where we draw the boundaries between different classes of astronomical objects. The broader scientific significance extends to astrobiology as well, though in a negative sense. KELT 9b represents an absolute extreme of uninhabitability, a world where life as we know it, or as we can even imagine it, is completely impossible. By understanding the conditions on KELT 9b and how they arise, scientists can better define the boundaries of the habitable zone around stars and understand what makes a planet capable of supporting life. Every hostile world we characterize helps narrow the search for potentially habitable planets by teaching us what to avoid. KELT 9b shows us that proximity to hot stars creates environments fundamentally incompatible with biology, helping focus the search for life on planets around cooler stars at greater distances. The study of KELT 9b also contributes to our understanding of exoplanet demographics and the statistical properties of planetary systems in the galaxy. By surveying large numbers of stars and determining what fraction host planets of various types, astronomers can infer the underlying processes that govern planet formation and can make predictions about the total number of planets in the Milky Way. Ultra-hot Jupiters like KELT 9b, while rare, are an important part of this census. Their rarity tells us something about the conditions required for their formation, and their properties provide constraints on theoretical models. Understanding the full distribution of planetary types, from cool habitable worlds to infernal planets like KELT 9b, is essential for building a complete picture of how common different types of planets are in our galaxy and universe. Finally, there is value in studying KELT 9b simply for the advancement of human knowledge and our collective understanding of the cosmos. The universe contains wonders and horrors beyond our everyday experience, and part of the scientific endeavor is to explore and understand these phenomena, regardless of their practical applications. KELT 9b may never be visited by humans, may never affect life on Earth in any direct way, and may not lead to immediate technological applications. But the knowledge that such a place exists, the understanding of the physical processes occurring there, and the intellectual achievement of characterizing a world 670 light-years away using only the light that reaches our telescopes represents a fundamental human accomplishment. Science is driven as much by curiosity and the desire to understand as by practical considerations, and KELT 9b satisfies that curiosity in profound ways. When we step back and consider KELT 9b in the context of the entire universe, the planet takes on an almost poetic significance as a reminder of both the vast diversity of cosmic environments and the relative tranquility of our own corner of the galaxy. The bigger picture that emerges from studying KELT 9b and other extreme planets is one of a universe far richer, stranger, and more varied than our ancestors could have imagined. A cosmos where planets range from frozen snowballs to worlds hotter than stars, where gravitational forces can tear planets apart, and where the delicate balance of conditions that makes Earth habitable is revealed as extraordinarily special. Our solar system, viewed in the context of the thousands of exoplanetary systems now known, appears increasingly unusual in its orderly arrangement. We have rocky planets in the inner system, gas giants in the outer system, relatively circular orbits with modest eccentricities, and no ultra-hot Jupiters or super-Earths, two of the most common types of planets found around other stars. The absence of a planet like KELT 9b in our solar system is not an accident or a sampling bias. It reflects the particular history of our system's formation and evolution. Whatever gravitational interactions occurred in the early solar system, they did not result in Jupiter or Saturn migrating inward to close orbits. Whatever disk processes operated did not create super-Earths between the orbits of Venus and Earth. Our system represents one outcome among many possible outcomes of planet formation. This realization has profound implications for how we think about Earth and our place in the cosmos. The fact that Earth orbits in the habitable zone of a relatively stable, sun-like star, with a circular orbit and conditions that have remained conducive to life for billions of years, emerges not as an inevitable outcome, but as a fortunate configuration that arose from the complex and somewhat chaotic process of planetary system formation. Had our solar system evolved differently, with giant planets migrating inward, or with a more massive sun that evolved more rapidly, Earth might never have existed as the habitable world we know, or might have been destroyed by gravitational perturbations. or rendered uninhabitable by changes in solar luminosity. KELT 9b serves as a stark counterexample to Earth, a world that demonstrates what happens when planetary system evolution takes a different path. The planet orbits a star hotter and more massive than our Sun, a star that will live for less than 1 billion years total compared to the Sun's 10 billion year lifetime. The planet itself has migrated to an orbit that ensures its destruction. Any rocky planets that might have existed in the system, any potential cradles for life, have likely been disrupted by gravitational interactions or sterilized by the intense radiation environment. The KELT 9 system represents a planetary system that went wrong from the perspective of habitability, a system where the conditions for life never arose or were destroyed early in the system's history. Yet from a broader perspective, there is no right or wrong in planetary system evolution. These are simply different outcomes of the same physical processes operating under different initial conditions. The universe does not favor habitable worlds over hellish ones. Both arise naturally from the laws of physics as they play out in different environments. KELT 9b is as valid and natural a result of planet formation as Earth, just representing a different branch of the vast tree of possible outcomes. The universe contains room for every possibility, from tranquil Earth-like worlds to infernal planets, like KELT 9b, to frozen ice worlds, to massive super-Jupiters, to tiny rocky worlds, huddled close to cool red dwarfs. The diversity of planetary systems also raises questions about how common habitable worlds might be in the universe. If planetary systems like ours are relatively unusual in their stability and configuration, does that mean habitable planets are rare? Or are there many pathways to habitability, with Earth-like worlds representing just one type among many possible habitable environments? The discovery of ultra-hot Jupiters, while showing us hostile environments, does not directly tell us about the prevalence of habitable worlds, but it does inform our understanding of planetary system dynamics and helps us estimate what fraction of systems might retain potentially habitable planets in stable orbits. Discoveries like KELT 9b also reshape humanity's cultural understanding of our place in the cosmos. For most of human history, Earth was thought to be the center of the universe, with all celestial bodies revolving around our world. The Copernican revolution displaced Earth from the center, but still left open the possibility that our solar system was typical, or that other worlds would resemble those in our system. The past few decades of exoplanet discoveries have completed another revolution in perspective, showing that our system is just one configuration among countless others, and perhaps not even a particularly common one. Planets like KELT 9b populate our galaxy in the thousands or millions, representing environments utterly alien to our experience, but no less real and no less deserving of study and understanding. This broader perspective also highlights the value of comparative planetology, the study of planets not just individually, but as a population, looking for patterns and relationships that reveal underlying physical principles. By comparing KELT 9b to other ultra-hot Jupiters, to cooler hot Jupiters, to planets around different types of stars, astronomers can identify which properties correlate with each other and which vary independently. Does higher stellar temperature always correlate with higher planetary temperature? Or do atmospheric properties sometimes decouple the two? Do all ultra-hot Jupiters show evidence of vaporized metals, or only those with certain compositions or masses? Do tidal effects dominate orbital evolution for all close-in planets, or only those around certain stellar types? These comparative studies gradually build up a comprehensive understanding of planetary physics that transcends any individual object. The study of extreme worlds like KELT 9b also serves an educational and inspirational function, capturing public imagination and communicating the excitement of scientific discovery. Most people will never work in astronomy or study planetary atmospheres professionally, but the idea of a planet hotter than many stars, a world where iron vaporizes and supersonic winds rage eternally, captures attention and stimulates interest in science. This educational value should not be underestimated. Today's students inspired by learning about KELT 9b might become tomorrow's scientists, engineers, educators, or simply informed citizens who appreciate the value of scientific inquiry. The sense of wonder that comes from learning about the extremes of nature is a powerful motivator for scientific literacy and engagement. Looking forward, the study of KELT 9b and similar planets will continue to evolve as new technologies and techniques become available. The next generation of extremely large telescopes, including the Extremely Large Telescope in Chile, the 30-meter telescope planned for Hawaii or the Canary Islands, and the Giant Magellan Telescope, also in Chile, will offer unprecedented capabilities for studying exoplanet atmospheres. These telescopes, with mirror diameters of 25 to 40 meters compared to current large telescopes' 8 to 10 meter mirrors, will collect far more light and achieve higher spectral resolution, enabling more detailed characterization of atmospheric composition, temperature structure, and dynamics. For a bright system like KELT 9, these capabilities could reveal subtle features in the atmosphere, track changes over time, and potentially even map atmospheric patterns across the planet's surface. Space-based observatories will also continue to play crucial roles. The James Webb Space Telescope, having begun operations relatively recently, will observe ultra-hot Jupiters, including potentially KELT 9b, providing infrared spectroscopy with unprecedented sensitivity. Future missions being planned, such as potential missions focused specifically on exoplanet characterization with coronagraphs or star shades to block stellar light, might eventually achieve direct imaging of planets like KELT 9b, seeing the planet itself rather than inferring its properties indirectly through transits and orbital variations. While technologically challenging, such observations would revolutionize our understanding by providing direct measurements of planetary temperature distributions, atmospheric features, and time variations. Theoretical advances will complement observational progress. Improved models of atmospheric dynamics will better capture the complex three-dimensional circulation patterns on tidally locked planets. More sophisticated chemistry models will include increasingly complete catalogues of atomic and molecular data, allowing more accurate predictions of atmospheric composition. Coupled models that simultaneously treat atmospheric circulation, chemistry, and escape processes will provide more self-consistent pictures of how ultra-hot Jupiters evolve. And increasing computational power will enable higher resolution simulations that can resolve smaller scale features and processes. The interplay between theory and observation, each informing and challenging the other, will drive progress in understanding KELT 9b and similar worlds. The ultimate fate of the KELT 9 system itself offers a sobering conclusion to our consideration of this planet. In a few 100 million years at most, KELT 9b will likely be destroyed, either torn apart by tidal forces as it spirals into the star, or completely evaporated by the intense radiation. The star, KELT 9 itself, burning through its fuel much faster than the Sun, will exhaust its hydrogen in another few 100 million to a billion years, leaving the main sequence and beginning its evolution toward becoming a red giant, and eventually a white dwarf. If KELT 9b somehow survives until the star expands, which seems unlikely, it will certainly be engulfed as the star swells to hundreds of times its current size. The planet's atoms will be incorporated into the star's outer layers, mixing with the stellar plasma and perhaps eventually being expelled in stellar winds to drift through space. On even longer timescales, the atoms that once comprised KELT 9b will be recycled through the galaxy's ecosystem of matter. They might become part of interstellar clouds, then be incorporated into new stars and planetary systems. Billions of years in the future, the iron atoms currently floating in KELT 9b's atmosphere might one day form part of a planet's core in some distant stellar system, not yet born. The hydrogen atoms might become part of the atmosphere of a habitable world, orbiting a star that hasn't yet begun to form. In this sense, nothing is truly destroyed in the universe. Matter is merely rearranged, cycling through different configurations as stars form and die, as planets come into being and are destroyed, as the great cosmic cycle of creation and destruction continues. As we conclude this exploration of KELT 9b, we are left with multiple perspectives on this extraordinary world. From a scientific perspective, KELT 9b is a natural laboratory providing insights into extreme physics and chemistry, a test case for theories of atmospheric dynamics and escape, and a data point constraining models of planetary system formation and evolution. From an aesthetic perspective, it is a world of terrible beauty, a planet that glows with its own light, where supersonic winds carry vaporized metals across hemispheres locked in eternal day and night, where the forces of nature operate at intensities that challenge comprehension. From a philosophical perspective, KELT 9b reminds us of the vast diversity of the cosmos and the precious improbability of our own world's habitability. The discovery and characterization of KELT 9b represents a triumph of human ingenuity and curiosity. Using instruments and techniques that push the boundaries of technology, astronomers have studied a world hundreds of light years away, determining its temperature, composition, atmospheric properties, and fate. They have watched as it loses thousands of tons of material every second, as it spirals slowly toward its doom, as it exists in conditions more extreme than almost anywhere else in the universe. And through this study, humanity has expanded its understanding of the cosmos, adding another chapter to the ongoing story of exploration and discovery that defines our species. KELT 9b is not just the most terrifying planet in the universe, though it certainly deserves that title. It is also a teacher, showing us the extremes of what nature can create. It is a reminder of both the vastness and variety of the cosmos and the special circumstances that allow worlds like Earth to exist. It is a challenge to our understanding, pushing theories to their limits and revealing gaps in our knowledge that motivate further research. And it is a source of wonder, a real place that exists right now in our universe, a planet so extreme that it defies imagination, yet is as real as the earth beneath our feet. In the end, perhaps the most important lesson from KELT 9b is that the universe is far stranger and more diverse than we can imagine. From our limited perspective on one small rocky planet, orbiting an ordinary yellow star in a quiet suburb of an average galaxy, there are worlds out there, thousands of them, millions of them, perhaps billions, each with its own story, its own properties, its own unique place in the cosmic landscape. Some are gentle and might harbor life. Others, like KELT 9b, are hellish beyond description. Together, they paint a picture of a universe teeming with worlds, a cosmos where every imaginable environment exists somewhere, where physics and chemistry play out in every possible variation. where the story of planets encompasses everything from tranquil habitable worlds to infernal spheres of vaporized metal, orbiting stars that will soon destroy them. And in studying all these worlds, from the most pleasant to the most terrifying, we fulfill our role as the universe, attempting to understand itself as conscious beings trying to comprehend the vast cosmos that gave rise to us and to worlds like KELT 9b, the planet where even atoms struggle to survive. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.